What's inside a black hole? It's one of the most haunting questions science has ever asked. Not because we know too little, but because we might never know at all. Black holes don't just hide information, they erase it, stretch it, burn it, and trap it behind a boundary we can never cross back from. The closer we get to the truth, the more reality itself seems to bend. Time slows, space warps, even light cannot escape. So tonight, we're going to explore this mystery, not with panic or urgency, but with wonder. We'll begin at the edge, the event horizon, and slowly fall inward, through layers of theory, into the heart of gravity. Past the place where physics begins to blur and imagination takes over, we'll ask the questions no telescope can answer. Is there a core, a tunnel, a hidden universe? Or is there simply nothing? Before we begin, let me ask you, where are you watching from tonight? And what time is it for you right now? Let us know in the comments. And if you enjoy drifting off to deep science, be sure to subscribe and help us reach 2,000 curious minds. Now take a breath. Let your body rest and allow your mind to drift, not outward, but inward. Because tonight, we are not traveling through space, we are falling into it, into the unknown, into the invisible, into a black hole. Chapter 1. The moment gravity collapses. It begins not with violence, but with stillness. A star once bright, once alive, runs out of fuel. For millions, sometimes billions of years, it's been burning, holding itself up by a delicate balance. Outward pressure from nuclear fusion pushes against inward gravity. A constant war, a perfect tension, but like all things, that balance eventually ends. The fuel runs dry, no more hydrogen to fuse, no more helium to ignite. And in that final breath, gravity begins to win. Slowly at first, then all at once. The star, no longer able to support its own weight, begins to collapse. Its outer layers fall inward, folding into themselves like a cosmic implosion. The core contracts, denser, hotter, tighter. If the star is small, it might become a white dwarf. If it's a little heavier, it might form a neutron star. But if it's massive enough, perhaps 20 or 30 times the mass of our sun, then something stranger happens. There is no known force in the universe strong enough to stop it, and so it collapses past every known boundary. Atoms are crushed. Electrons collapse into protons. Protons collapse into nothing we can measure. And at some point, an invisible, irreversible point, a black hole is born. We call that boundary the event horizon. It's not a wall or a surface. It has no texture, no color, no sound, but it marks the line between what can be known and what can never return. From the outside, the star appears frozen in time. To a distant observer, it seems to hover at the event horizon forever, its light stretched thinner and redder, as it tries to escape the gravity well, slower, dimmer, until it fades completely. But from the star's own point of view, the collapse continues, inward, relentlessly. Gravity doesn't stop at the surface. It pulls everything to the center, to a single point of infinite density. We call that point a singularity. It is not a place. It is not a thing. It is where the equations break, where time, space, and mass lose meaning. And yet, according to general relativity, it must exist, because there is no other way to describe what happens when all matter collapses to zero volume and infinite density. But here's the truth we must accept as we begin this journey. We don't know what a singularity really is. No one does, because no one has ever seen inside a black hole, and no information from within has ever escaped. The laws of physics as we understand them simply stop working there, and that is where the mystery begins. But let's stay for a moment longer on the outside. Let's talk about what we do know. A black hole is not a hole in the usual sense. It's a region of space. A field of gravity so strong that nothing, not even light, can escape its pull. The size of this region depends on the mass of the black hole. We call this boundary the event horizon, and its radius is known as the Schwarzschild radius. For a black hole the mass of our Sun, that radius would be just under 3 kilometers, which means all the mass of a star 1,000,000 kilometers wide has been crushed into something the size of a small city. And yet, from the outside, a black hole is strangely simple. It can be fully described by just 3 things: its mass, its spin, and its electric charge. No matter how complex the star was before collapse, its chemical makeup, its magnetic field, its motion, almost all that information is lost. Only mass, spin, and charge remain. This is what physicist John Wheeler meant when he said, "Black holes have no hair. They're smooth, featureless, and unforgivingly anonymous." But the real strangeness begins at the boundary. Imagine hovering just above the event horizon. From that distance, time moves differently. Slower, heavy. According to general relativity, as you approach the horizon, time itself begins to dilate. An outside observer would see your clock tick more slowly. Closer still, your seconds become minutes, then hours, then days, until finally at the very edge, time. From your perspective, nothing unusual happens as you pass the horizon. There's no sudden jolt, no impact, no bright flash. You cross it without noticing. But from the outside world, you vanish. You appear frozen at the edge, faded, stretched. Your last signal never quite reaches out. It hovers, slowing, until it disappears into silence. This strange division between what is observed inside and what is seen from outside is what makes black holes so hard to grasp. They do not just bend light, they bend experience. They warp meaning itself. Now imagine that collapse from the inside, not as a spaceship, not as a person, but as space itself. Because a black hole doesn't just pull on matter, it pulls on geometry. It curves the very shape of the universe. In some models, falling into a black hole is like sliding down a funnel of warped space. Deeper, narrower, tighter. The walls become steep, the center becomes sharp, and the bottom is unknowable. Some have compared it to the drain of a cosmic whirlpool. Others describe it as a one-way portal, a region where all paths lead only inward, where escape is no longer a direction you can choose. You don't fall toward the singularity. You fall in time, toward the future. And in a black hole, all futures end at the same point. That's what makes it so strange. A black hole is not just a prison of space. It is a trap of time. And yet, for all its finality, a black hole is still a part of the universe. It can orbit, it can move, it can even merge with other black holes. We've observed the ripples from such collisions, gravitational waves traveling across the cosmos, shaking detectors on Earth with signals from millions of years ago. A brief tremor, a distant echo, a whisper from the edge of known physics. We've also taken a picture, an actual image of a black hole's shadow, surrounded by glowing plasma, captured by a planet-wide array of telescopes. It confirmed what we believed, and yet somehow deepened the mystery, because even as we see its shadow, we still cannot see what's inside. Some theories say the singularity is a true point of infinite density. Others argue it is smeared, fuzzed out by quantum uncertainty. Some believe it hides a wormhole. Others think it stores the information in ways we haven't yet discovered. One theory says the information is burned onto the event horizon itself, encoded in the surface, like a cosmic hologram. We'll explore all of those ideas in the chapters ahead. But for now, let's sit with this. Every black hole began as something else, a star, a sun, a glowing living engine of light, and every one of them collapsed, not in chaos, but in order, following the rules of gravity, obeying the structure of the universe, until they became something the universe itself can no longer fully explain. So as we begin this descent together through time, through space, through theory, remember this: a black hole is not just a question in physics, it is a mirror, one that reflects the limits of our knowledge, and perhaps something even deeper. In the next chapter we'll move closer to the edge, to the boundary between light and silence, to the event horizon. Chapter 2. What is a singularity? To understand what lies at the heart of a black hole, we must confront one of the strangest and most unsettling concepts in all of physics, the singularity. Unlike planets or stars or even atoms, a singularity is not a thing we can see, measure, or even describe in normal terms. It is not made of matter in the way you and I are, nor does it have a shape or a surface or a location that exists in any traditional sense. Instead, it is the name we give to a point, a single infinitesimal point, where everything we know about space, time, and physics begins to fall apart. When scientists speak of a singularity, they do not mean a physical object like a rock or a planet or even a particle. They are speaking of a location where density becomes infinite, where gravity becomes infinitely strong, and where the known laws of nature break down completely. In mathematical terms, it is where the curvature of space-time becomes infinite, a value that cannot exist in any equation without destroying the equation itself. General relativity, the theory that describes gravity and the motion of massive objects, predicts that when enough mass collapses into a small enough region, space-time itself is crushed into this singular, undefined point. But what does that actually mean? To fall into a black hole is to fall toward this singularity, not just through space, but through time itself. You are not simply moving closer to the center. You are being pulled through a region where every path, every possible trajectory, leads to the same unavoidable fate. No matter which direction you choose, you are always falling inward, because inside a black hole, inward is not just a direction, it is the future. Imagine space and time as a fabric, smooth and curved. Under normal conditions, a star creates a dent in that fabric, a curve that guides the motion of planets and light. But when a star collapses into a black hole, it is as though that dent becomes a funnel, and the funnel doesn't stop at any flaw. It keeps narrowing. It keeps stretching. It keeps pulling until the very fabric tears. That tear, that point where space and time no longer function, is the singularity. And yet, despite how often it appears in theory, the singularity remains one of the most mysterious features in all of modern science. That is because it represents a failure, not of nature, but of our understanding. Whenever our models produce infinities, it is a sign that something is missing, something deeper, more fundamental, not yet discovered. General relativity tells us the singularity must exist, but quantum mechanics, the theory that governs the very small, refuses to accept it. According to quantum theory, nothing can be perfectly precise. Nothing can be squeezed to an infinitely small point. There must always be uncertainty, always a limit to how well we can define a particle's location. And so when these two great theories of physics collide, one describing massive objects like stars and galaxies, the other describing the tiniest building blocks of matter, they produce incompatible answers. General relativity says, the singularity exists, and space-time ends. Quantum mechanics says, infinities don't exist, and space-time cannot end like that. This tension between the two theories has haunted physics for over a century. It is why the singularity remains hidden, not just by distance or darkness or gravity, but by our own incomplete understanding of how the universe works at its deepest level. Some scientists believe that when we finally discover a theory of quantum gravity, a single, unified description that includes both quantum mechanics and general relativity, the singularity will vanish, not because the black hole will disappear, but because the point we once thought was infinite will turn out to be something else, something new, something real. Perhaps it is not a point at all, but a structure, something that occupies space in a different way. Perhaps it is a knot of strings, as suggested by string theory. Perhaps it is a looped geometry, as in loop quantum gravity. Or perhaps it is not an object, but a condition, a state of the universe in which the normal rules no longer apply, and time and space no longer behave in ways we can imagine. Until we have that theory, we are left with approximation. According to current models, the singularity lies at the very center of a black hole, a mathematical point where mass is infinitely concentrated. But we must be careful with that word center. It suggests a place you could point to, a position you could approach, as if from outside. But inside a black hole, space and time are twisted. The singularity is not ahead of you or below you. It is in your future. No matter where you are inside the event horizon, the singularity lies ahead, like tomorrow, like your destination, like a moment you are moving toward and cannot avoid. And so, the deeper you fall, the closer you come. But you never observe the singularity from a safe distance. You cannot hover near it or study it from afar. Because to be near it is to be in it. To reach it is to enter. The equations tell us that as you fall toward the singularity, tidal forces grow stronger. These are the differences in gravity between one part of your body and another. If the black hole is small, the tidal forces will rip you apart long before you reach the center, a process known as spaghettification, where your body is stretched into a long, thin strand of matter. But if the black hole is large enough, if it is millions or billions of times the mass of the sun, the tidal forces at the event horizon may be weak. You might not feel them. You might pass the boundary calmly, without pain, and yet, no matter how gentle the fall may seem, the end is still the same. Once inside, all paths lead inward. Time carries you forward, and forward, inside a black hole, leads to only one place, the singularity. But is the singularity truly the end? That question remains open. Some physicists believe that singularities are not real, that they are merely artifacts of incomplete theories. They argue that what we call a singularity is actually a signal that new physics is required. Just as the ultraviolet catastrophe of classical physics led to the birth of quantum mechanics, perhaps the singularity is pointing us toward a deeper understanding of the universe. Others believe the singularity is a boundary not just for matter and energy, but for space and time itself, a place where time ends, a place where causality breaks down, a place where the distinction between past and future dissolves. Still others imagine more radical possibilities. Could the singularity be a gateway? Could it connect to another part of our universe, or even to another universe entirely? Could black holes be bridges to something else, tunnels through the fabric of reality? These are not answers, they are questions, speculations, hints, and yet we must consider them, because the singularity, whatever it is, represents a frontier. It is the edge of what we can calculate, the boundary of what we can know. It marks the point where our tools stop working, and our curiosity begins to drift into the unknown. To explore it is not just to study physics, it is to ask what reality truly is. It is to ask whether space and time are continuous or discrete, whether matter can be infinitely divided, whether information is ever truly lost. And so, as we continue our descent into the black hole, let us remember that we are not merely exploring an object. We are exploring a paradox, a conflict between the known and the unknown, a riddle that has resisted answers for decades, a silence that no signal can break. In the next chapter, we will move closer to that boundary, not the singularity, but the line that surrounds it. A line that does not mark the end of space, but the end of return. The event horizon, what happens there, will challenge everything we think we understand about time, light, and causality. Let's begin. Chapter 3: The Event Horizon, where time stops. The event horizon is not a surface you can touch. It has no texture, no edge, no resistance. There is no flash of light, no visible line, no sudden jolt when you cross it. And yet, it may be the most important boundary in the known universe, not because of what it is made of, but because of what it separates: the known from the unknowable, the visible from the invisible, the reversible from the irreversible. When we speak of the event horizon, we are describing the threshold that surrounds a black hole. It is the point at which escape becomes impossible, not because of some wall or barrier, but because the geometry of space-time itself has shifted so dramatically that all possible paths curve inward. Once something crosses this boundary, whether it be an aim of light, a grain of dust, or an entire star, it is lost forever to the outside world. No signal can escape, no information can return. From our perspective on the outside, it has fallen into silence. But this silence is not immediate. It is gradual. It is stretched. Imagine for a moment watching an object fall into a black hole. Perhaps it is a spaceship, or a satellite, or a probe. As it approaches the event horizon, something strange begins to happen. Its motion appears to slow down. Its signals become more faint. The light reflecting off its surface becomes redder and dimmer. From your point of view, standing far away, it never quite crosses the line. Instead, it hovers there, frozen in time, suspended at the very edge, stretched and dimmed until it fades from view completely. This effect is not a trick of the eye. It is a consequence of Einstein's general theory of relativity. The closer an object gets to a massive body, the more time slows down in its reference frame relative to a distant observer. Near a black hole, this difference becomes extreme. At the event horizon, time appears to stop altogether, not for the falling object itself, but for those watching from afar. To them, the object is caught in a moment that never ends. But what does this mean for the object falling in? From its own perspective, time continues normally. Its clocks tick forward. Its thoughts move in sequence. It passes the event horizon without feeling anything unusual. There is no force that pushes back, no sudden rupture. The horizon is not a wall, it is simply a point of no return. This discrepancy between what is seen from the outside and what is experienced from the inside is what makes the event horizon so mysterious. It is not merely a boundary in space. It is a boundary in perception, a fracture in how reality is experienced depending on where you stand. Now consider what this means for light. Normally, light travels in straight lines, or more precisely, in the shortest possible path through curved space. Around a massive object like a planet or a star, light bends slightly. Around a black hole, the bending becomes extreme. Some light escapes, curving gently. Some is trapped in circular orbits, endlessly spiraling. And some crosses the horizon, never to emerge again. At the event horizon, the escape velocity equals the speed of light. To break free, something would have to move faster than light itself, and according to the laws of physics as we know them, this is impossible. So light, which always moves at the cosmic speed limit, finds itself forever caught. It cannot return. It cannot deliver its message. It becomes part of the silence. This silence has profound consequences, because if no light, no information, and no influence can escape the event horizon, then everything inside becomes hidden from the rest of the universe. It is not simply distant, it is cut off, isolated, causally disconnected. Whatever happens beyond that line can never affect the outside again. not directly, not through force, not even through light. This raises difficult questions. If information falls into a black hole and cannot return, is it truly lost? Something once existed, a planet, a signal, a person, and it crosses the horizon. Does the universe forget it? Does that information vanish forever? Stephen Hawking once proposed that it does. That black holes destroy information, that the laws of quantum mechanics, which insist that information must be conserved, are violated at the edge of a black hole. This suggestion sparked a decades-long debate, a paradox that still divides physicists today, because if black holes truly erase information, it would mean that physics, at its deepest level, is incomplete. Other scientists have suggested alternatives. Perhaps the information is not lost, but scrambled beyond recognition. Perhaps it is stored on the surface of the event horizon itself, encoded in a way we do not yet understand. This idea gave birth to the concept of the holographic principle, the notion that all the information contained within a volume of space can be described by information encoded on its boundary. In this view, the event horizon is not just a point of no return, it is a memory, a shell, a skin of information that records everything that has ever crossed it. From this idea emerged the notion that the universe itself might be a hologram, not in the sense of an illusion, but in the sense of a projection, a reality defined not from within, but from its edges. Still, these are ideas, theories, frameworks. No one has ever crossed an event horizon and returned. No probe has survived the journey. No telescope has seen past the veil. What we know of the event horizon comes from equations, from simulations, from the strange consistency between mathematics and observation. And yet, we have observed that. We have witnessed the outline of a black hole, captured by radio telescopes spanning the globe, a glowing ring of gas, orbiting a shadow, a void where light cannot return. We have felt their presence through gravitational waves, the ripples in space-time caused by the collision of black holes, carrying with them the faint signature of horizons, merging, forming something deeper, darker, and more permanent. So what is the event horizon, really? It is not a surface, it is not a thing, it is not made of atoms or particles. It is a threshold, defined by gravity, shaped by space-time, and ruled by light. It is the line you cannot cross without falling in. It is the last moment anything in the universe can be part of our story. It is the edge between knowledge and mystery, between cause and consequence, between what we see and what we never will. To approach it is to approach finality. To cross it is to surrender to gravity, completely. To reach it is to find that even time itself can be pulled, stretched, and stopped. And yet, for something so final, the event horizon is surprisingly calm. There is no violence at the boundary, no explosion, no rupture in the laws of physics. The real drama happens not at the surface, but beneath it. The real questions are not about what happens when you cross the line, but about what happens after, what lies ahead, what you are falling toward. Because the event horizon is not the end, it is only the beginning of a one-way path inward, deeper and deeper, toward a region where our theories no longer apply, where quantum particles clash with gravity, where time may loop, stretch, or dissolve. In the next chapter we will begin that descent. We will step past the horizon, and we will imagine what it would feel like to fall forever, toward the unknown. Chapter 4, Falling In. What would you see? Imagine, just for a moment, that you are not reading about a black hole from the comfort of Earth, or watching it on a distant telescope's feed, but that you are approaching one, slowly, deliberately, with full awareness of what lies ahead. You are aboard a quiet craft, drifting through the vast dark of interstellar space, and in front of you looms a perfectly black sphere, a region where no light escapes, no signals return, No stars shine. Around it, glowing plasma spirals like water circling a drain, heated to incredible temperatures as it races at nearly the speed of light. The black hole does not pull you like a magnet, and yet everything about it draws you in, not just gravitationally but psychologically, philosophically, irresistibly. As you approach, the light around you begins to behave strangely. The stars behind you stretch and smear, their positions distorted by the extreme warping of space. Light does not move in straight lines anymore. Paths curve inward, bend around you, twist like ribbons pulled by unseen hands. The black hole's gravity distorts not just the stars, but the very fabric of reality itself, as if you are falling into a dream where geometry no longer obeys the rules. If you glance to the side, the sky appears to wrap around the black hole in a halo of fire. That is the photon sphere, a narrow ring where light can orbit the black hole in perfect circles, balanced on the edge between escape and capture. In that ring, a photon could travel forever, neither pulled in nor pushed out, caught in a limbo that only this extreme gravity could allow. But you are not in the photon sphere. You are moving closer. The event horizon grows larger in your view, not like a planet you're descending toward, but like a future you cannot avoid, expanding, engulfing, inevitable. There is no sound, no warning, no alarm. Space is silent. But in the instruments around you, time begins to slow. If you look at the clock on your ship, it ticks forward like normal. But if you could somehow observe the universe behind you, the outside world, the galaxies, the stars, the people you left behind, you would see that their clocks are ticking faster. Minutes pass for you, while years pass for them. Time is stretching apart. This is not a trick of your eyes. This is not cinematic drama. This is real, measurable, and predicted precisely by Einstein's equations. You are not just moving through space. You are falling through time. Now, as you pass the event horizon, something profound happens, and yet you feel nothing. No bump, no shimmer, no transition. There is no surface here, no impact, no indication that a boundary has been crossed. One moment, the outside universe was still reachable, distant, distorted, but present. The next moment, it is gone. Not because it has vanished, but because the paths through space no longer lead outward. Every direction now leads inward. The horizon is behind you, and there is no going back. This is where physics becomes strange. This is where intuition fails. Inside the event horizon, space and time trade roles. The radial direction, the one pointing toward the center, becomes time-like. That means it behaves like time normally does outside. It only moves forward. You cannot stop moving toward the center any more than you could stop tomorrow from arrival. No matter how powerful your engines, how strong your resistance, how clever your escape plan, you are already moving toward the singularity, and there is nothing in the laws of physics that can prevent it. Still, from your perspective, time feels normal. You can breathe, think, you can examine your surroundings. You can even imagine turning around, though turning around has no meaning anymore, because backward is not a direction that leads to freedom. You can rotate, but you cannot reverse your descent. Down is forward. Inward is destiny. And what would you see? The view inside a black hole is one of the most debated and speculative questions in modern physics, because we cannot observe it directly. But we can imagine, we can calculate, we can trace the paths of light rays, simulate trajectories, and visualize what the laws of physics suggest. If the black hole is rotating, and most of them likely are, then the geometry inside becomes even more bizarre. The singularity is not a point, but a ring, a spinning loop of infinitely dense matter, around which space-time is dragged like syrup around a twirling spoon. This effect, known as frame dragging, means that even if you try to remain still, Space itself is moving beneath you. You are caught in a flow of space-time, like a raft in a river with no shore. As you fall deeper, the light from the universe outside shrinks to a small, distorted patch behind you. It is still there, but it is compressed, dimmed, and redshifted to extremes. The rest of your view is curved inward, toward the center, toward the place where all paths lead. Shadows twist in impossible ways. Objects seem to move without moving. Directions lose meaning. But perhaps the strangest thing is this: from your own perspective, you are not dying. You are not being torn apart, at least not yet. You are simply falling. Smoothly, calmly, quietly. Gravity is not a force pushing on you. It is the shape of space pulling you along. You are in free fall, the purest kind, the most perfect kind. The kind Einstein described not as a sensation, but as its absence. You feel weightless. You feel nothing. And that, in itself, is deeply unsettling. Because the laws you once trusted, Newton's laws, even Einstein's laws, no longer protect you. The clock is still ticking, but every tick brings you closer to a place no theory can describe. You are crossing a region of space-time where no observer outside can follow, where no information can be shared, where your future is sealed by the curvature of reality itself. Some models suggest that, inside the black hole, distances become irrelevant, that time accelerates, that the singularity arrives quickly, perhaps in seconds, perhaps in less, and that nothing survives the encounter. Other models, especially those involving very large black holes, suggest a longer journey. Perhaps you have minutes, perhaps hours. It depends on the mass of the black hole and the path you follow inside. But whatever the timeline, the destination is the same. You are falling toward a place where the known laws of nature collapse, a place that may not even be part of our universe anymore, a place that might not be a place at all. And yet you see nothing of this. You see darkness, perhaps, or strange patterns of warped light, or nothing at all, because perception itself begins to break down. Your instruments fail, your signals are useless, you are alone. Not just physically, but causally. You are no longer part of the same reality as the rest of the universe. From the outside you have disappeared, not because you have stopped existing, but because you can no longer affect the world you came from. You are still falling, still thinking, still alive in some theoretical sense, but that life is cut off, isolated, unreachable. You are a story that can no longer be told, and that raises one final question, one we cannot yet answer. Do you ever reach the singularity, or does something else happen before you arrive? Is there a firewall, a region of quantum chaos that burns you to information ash? Is there a bounce, a quantum rebound that sends you into another universe? Is there a remnant, a frozen core that stores your data in some unknown way? Or is there simply an end? In the next chapter we will move deeper into this puzzle. We will explore what might happen not just to objects, but to information, to light, to time itself, once it has passed the point of no return. Because the deeper we fall, the stranger the questions become, and the more the black hole stops being an object and starts becoming a question. Chapter 5: Spaghettification and Tidal Forces. As you continue your fall beyond the event horizon, something begins to change. Not all at once, not with the violence you might expect from science fiction, but gradually, steadily, like a quiet tide rising around your body. You may not feel it at first. You may still be weightless, still adrift in the calm silence of curved space. But the deeper you fall into the black hole, the more the invisible forces around you begin to diverge. And those differences, those subtle but growing imbalances, are not just theoretical, they are real. They are physical, they are deadly. This is where the strange term spaghettification comes into play, a word that sounds almost humorous, almost light-hearted, until you understand what it really means. Spaghettification is a name physicists have given to the process by which matter, including you, is stretched and compressed by the intense tidal forces of a black hole. And once you understand the mechanism behind it, you realize that it is not a joke at all. It is one of the most extreme consequences of gravity in the universe. Tidal forces occur because gravity is not the same strength everywhere. If you are standing on Earth, your feet are closer to the center of the planet than your head is. That means your feet are pulled just a little bit harder toward the center than your head is, not enough to notice in daily life, but enough to produce tides in the ocean, to affect the shape of Earth's crust, to gently stretch and compress your body without your awareness. But near a black hole, those differences in gravitational pull, the tidal gradients, become dramatically amplified. The difference in force between your head and your feet is no longer slight. It becomes enormous. As you fall feet first into a black hole, gravity pulls on your feet harder than it pulls on your head. The deeper you fall, the stronger that difference becomes, and it doesn't just pull, it stretches. At the same time, the gravitational field is also compressing your body from the sides. It is squeezing you horizontally while stretching you vertically, distorting your shape into something long, thin, and impossibly fragile. You are no longer a person in the conventional sense. You are being drawn into a filament, a strand, a string of atoms that is longer than it should be, narrower than it can survive being, and exposed to forces that no biological structure can endure. This process does not happen instantly. Its intensity depends on the size of the black hole. For small black holes, only a few times the mass of our Sun, the tidal forces at the event horizon are already extreme. You would be torn apart before even crossing the boundary. But for larger black holes, especially the supermassive ones found at the centers of galaxies, the tidal forces at the event horizon are surprisingly gentle. You could pass through the horizon without being harmed. But the deeper you go, the worse it gets. No matter how slowly the process begins, it always ends the same way, with complete disintegration. And this disintegration is not like falling apart or being crushed. It is a fundamental unraveling. The atomic bonds that hold your body together, the forces that keep your cells, molecules, even your nuclei intact, are overwhelmed by gravity. No force you know can resist it. Not chemical bonds, not electromagnetic repulsion, not the strong nuclear force. Gravity at this scale is king, and it does not negotiate. What makes this experience even more alien is that it happens in silence. There is no sound in space, no scream, no echo. There is only motion, the quiet, unstoppable motion of descent. You are not being pushed or thrown or ripped in a cinematic way. You are being stretched by geometry itself. Your atoms are still following the paths they are supposed to follow. It is just that those paths now lead in different directions, and those directions are pulling you apart. This is the strange, almost paradoxical truth of tidal forces in a black hole. They are not acting upon you in the traditional sense. You are in freefall, you are weightless, and yet you are being destroyed, not by a force pressing down on you, but by the sheer curvature of space-time. The space your body occupies is no longer flat. It is no longer uniform. It is no longer safe. And the larger your body is, the more it is subjected to these distortions. There is a kind of beauty in this process, a terrifying, inescapable beauty. You are becoming part of the black hole. Your structure is breaking down, not into debris, but into alignment. You are being streamlined, aligned with the gravitational field, reshaped into the narrowest possible configuration for entry. You are not just falling, you are being sculpted by physics, turned into a perfect thread of matter, destined for the singularity. And yet, as strange as it sounds, this process is not unique to you. It happens to everything. It happens to particles, to atoms, to radiation. Anything that crosses the horizon will, if it survives long enough, be subjected to the same fate. It will stretch, it will narrow, it will spiral inward, it will collapse. In this way, the black hole consumes, not like a mouth, not like a monster, but like a pattern, a mathematical inevitability. There is no anger in it, no violence in the emotional sense, only the cold, flawless consistency of Einstein's equations, applied at their most extreme. The black hole is not trying to destroy you, it is simply following the rules of gravity, and you are now one of the things governed by those rules. If you could observe your own fall, if somehow you had the perspective to look at yourself from a stable frame, you would see your body becoming longer and thinner, disappearing into the singularity like a hair drawn into the center of a whirlpool. And if you could measure the forces acting upon you, you would see numbers that climb without end. The closer you get to the singularity, the stronger the tidal forces become, until they reach levels so absurdly high that the very concept of force loses meaning. It is not just your body that cannot survive, it is your definition of structure itself. And this is where the black hole reveals one of its final truths, that scale does not protect you, that mass, motion and resistance mean nothing in the face of infinite curvature. The black hole does not care how big or small you are. Everything becomes spaghettified, everything is reduced. Some physicists believe that in those final moments before you are compressed into quantum oblivion, something deeper happens. Perhaps your information, your structure, your identity is somehow preserved, not in your body which no longer exists, but in the gravitational field, in the quantum state of the horizon, in some subtle, invisible way that we do not yet understand. Others believe that nothing is preserved, that what crosses the horizon and enters the singularity is that spaghettification is not just a physical process, but a metaphysical one, the absolute end of individuality, of causality, of meaning. We do not know. We cannot know, not yet. But we do know this. The process of falling into a black hole is not like falling into a pit. It is not like descending a staircase. It is not like traveling through darkness. It is more like entering a new kind of reality, one governed by different rules, one where direction and force and time are all subject to change, to distortion, to collapse. Spaghettification, as strange as it sounds, is only the physical symptom of a deeper truth, that black holes are not just objects, they are transformations. They do not simply destroy, they change the meaning of what it is to exist. In the next chapter, we will rise above the fall. Not physically, for that is no longer possible, but conceptually. We will take a step back and ask from the outside, what would all of this look like? What would a black hole appear to be to those who never cross the line? Because the story of a black hole is not only the story of what falls in, but of what is seen from the edge. Chapter 6. The view from the outside. From the inside, a black hole is silent, final, unreachable. But from the outside it tells a different story, one shaped not by destruction but by mystery, because even though no light escapes from within, a black hole still exerts an undeniable influence on the space around it. And that influence is not hidden. It is observable. It is real. It is how we first knew black holes existed, long before we ever saw one. To understand what a black hole looks like from the outside, you must first understand that black holes do not exist in isolation. They are part of galaxies. They live in systems. They orbit other stars. They interact with the environment around, and in doing so they leave fingerprints, not in light, but in motion. The earliest evidence for black holes did not come from telescopes that captured their image directly. It came from the behavior of stars, stars that were orbiting something invisible, something massive, something with such immense gravity that only a black hole could explain their speed. In binary systems, astronomers saw one bright star circling an unseen companion. That companion emitted no light, yet its mass was clear. The orbiting star's motion told the story. Something was there, something dense, something dark. This is how black holes first announced themselves, not by what they revealed, but by what they concealed. They are not visible, but their gravity is. They cannot be seen, but their influence cannot be ignored. Later, with the development of high-energy telescopes, astronomers began to see more. They detected intense X-rays coming from regions of space where nothing should be shining. These X-rays were not coming from the black holes themselves, but from the matter surrounding them, matter that was heating up as it spiraled inward, forming what is known as an accretion disk. As gas and dust fall toward a black hole, they do not plunge straight in. They spiral, forming a disk that compresses, collides, and heats to millions of degrees. That heat produces radiation, not gentle visible light, but violent, high-energy X-rays. And those X-rays scream out into the universe, visible to instruments tuned to their signal. So even though black holes are dark, the space around them often glows with violence. They are not black voids floating peacefully in space. They are engines, furnaces, regions where matter is crushed, where light is bent, where time is altered. And then in 2019 came the moment that changed everything, the first direct image of a black hole's shadow, captured by the Event Horizon Telescope, a network of radio telescopes spanning the globe. The image showed a glowing ring of light surrounding a central darkness. That ring was the last light escaping before falling inward, bent by the black hole's gravity into a circle. The darkness at the center was not the black hole itself, but its shadow, the region from which no light could reach us. That image was not just a photograph. It was a map of extreme physics. It was a confirmation of theory. It was the visual proof of an object predicted by Einstein's equations over a century before. But even more than that, it was a glimpse of something profound, not just what the black hole is, but how it looks to us, from here, from outside, from the relative safety of normal space-time. And what do we see? We see curvature. We see distortion. The light around a black hole does not travel in straight lines. It bends, warps, stretches. It forms arcs and rings and illusions. If you were to look at a bright star directly behind a black hole, you would still see it, not because the light passed through the black hole, but because it was bent around it. This bending of light, called gravitational lensing, turns black holes into natural telescopes, magnifying and distorting the background universe. In extreme cases, it creates multiple images. A single star might appear in two places, or as a ring of light, a phenomenon known as an Einstein ring. These effects are not just curiosities, they are tools. By studying the way black holes bend light, scientists can measure their mass, their spin, their geometry. But the view from the outside is not just visual, it is temporal. As we watch something fall toward a black hole, its motion slows, not because it is actually slowing down, but because time in our frame is stretching. From our perspective, the falling object never quite reaches the horizon. It appears to hover, frozen in time, its light becoming redder and dimmer as the black hole's gravity stretches its wavelengths. This process, known as gravitational redshift, turns visible light into infrared, then into radio, then into silence. Eventually, the object fades completely. It disappears not in an instant, but in a gradual erasure, a soft fading into darkness. And yet, from the falling object's point of view, nothing unusual happens. Time continues. The crossing occurs. The journey goes on. This mismatch between what the falling traveler experiences and what we observe is one of the strangest features of black holes. It is not just a trick of distance. It is a deep truth about how time behaves under the influence of gravity. From the outside, we see the effects. We see the matter heating up. We see the X-rays. We see the accretion disk glow. We hear the gravitational waves, ripples in the very fabric of space-time when black holes collide. But we never see the interior. We never see past the horizon. We never know what happens next. That barrier is absolute. It is not technological. It is not a limitation of our instruments. It is a limitation of the universe. The event horizon marks the boundary, not just of observation, but of causality. Beyond it, nothing can influence us. No signal can reach us. The black hole is not just hidden. It is disconnected. It is cut off. And yet, it radiates something more than light. It radiates questions. From the outside, the black hole is a puzzle, one that refuses to be opened. It challenges our understanding of gravity, of information, of entropy, of time. It forces us to confront the limits of our theories. It demands a reconciliation between general relativity and quantum mechanics, a reconciliation that has not yet been achieved. It is because of black holes that we question the permanence of information. It is because of black holes that we wonder whether space-time is continuous or pixelated. It is because of black holes that physicists propose bold, unsettling ideas that the universe is holographic, that reality is emergent, that the fabric of everything might be woven from something far stranger than we ever imagined. And all of this, every theory, every model, every paradox begins with the simple act of observing, watching the way light bends, watching the way stars move, watching the way reality itself seems to curve. The view from the outside is not just a sight, it is an insight. It is a window into deeper laws, into unresolved contradictions, into the edge of what is knowable. We stand here, on the outside, and we ask what lies within. We measure, we calculate, we theorize, but we cannot know, not directly, not yet. Because to truly know what happens inside, you would have to fall in, and if you fall in, you cannot come back. In the next chapter, we will explore the black hole from a different angle, not as a place of gravitational force, but as a solution to Einstein's field equation. We will look at the mathematical foundations of how black holes bend reality, and how general relativity predicted their existence long before we ever saw their shadow. Because the black hole was not discovered by accident, it was foreseen. Chapter 7: Black Holes in Einstein's Universe. Long before black holes became headlines, before they were captured by telescopes or hinted at through gravitational waves, they were quietly waiting inside the mathematics of general relativity. Not discovered through experimentation, but predicted by pure thought, as a consequence not of speculation but of geometry itself. These objects, these strange lightless traps in space, were not the invention of science fiction. They were the inevitable result of Einstein's revolution, a revolution that forever changed how we understand space, time, mass, and gravity. In 1915, Albert Einstein introduced his general theory of relativity, a framework that redefined gravity not as a force, but as the curvature of space-time caused by mass and energy. According to this theory, massive objects do not pull other objects with invisible strings. Instead, they warp the fabric of the universe around them, bending the paths of light and matter, not because they exert a force, but because those objects are simply following the straightest possible lines through curved space. This insight that gravity is geometry opened the door to a new way of seeing the universe. And it also opened a door to something stranger, something darker, something Einstein himself was hesitant to embrace. Only a year after Einstein's theory was published, a German physicist named Karl Schwarzschild found a solution, an exact mathematical solution to Einstein's equations that described what would happen if a massive, non-rotating, uncharged object collapsed into a point. His solution described the space-time around such an object and revealed something deeply unsettling. There existed a radius, now called the Schwarzschild radius, inside of which escape would be impossible. Not because the equations broke down, but because the geometry demanded it. This radius would become known as the event horizon. Schwarzschild's solution showed that if enough mass were compressed into a small enough volume, space-time would curve so steeply that all paths would point inward. Light, matter, and even time would fall toward the center, and once past the event horizon, nothing could return. At the time, this idea was met with skepticism. Einstein himself doubted whether such objects could ever form in nature. He saw the mathematics but resisted the physical implication that the universe could allow such complete collapses. The concept seemed too extreme, too unphysical, too final. And for decades, black holes remained mathematical curiosities, solutions on paper, but not yet part of the observable universe. But the equations were unambiguous. General relativity predicted that under certain conditions, especially in the case of massive stars, gravitational collapse would not stop. There would be no pressure strong enough, no fusion reaction hot enough, no structural limit high enough to resist the inward pull of gravity once a critical threshold had been crossed. The collapse would continue, beyond atoms, beyond nuclei, beyond any known form of matter, until it reached the point of no return. And when that happened, the geometry of space-time would form a region where all future paths led to a single point. The singularity. This was not a philosophical statement, it was not poetic metaphor, it was what the math demanded. In the 1930s, physicists like J. Robert Oppenheimer and Hartland Snyder took Schwarzschild's solution seriously and began modeling what would happen to real stars as they exhausted their fuel. Their calculations showed that black hole formation was not only possible, it was inevitable. If a star was massive enough and lacked the internal pressure to resist collapse, general relativity required that it would form a black hole. Still, it wasn't until the second half of the 20th century that black holes moved from fringe, theoretical ideas to serious astrophysical contenders. In the 1960s and 70s, a new generation of physicists, including Roger Penrose, John Wheeler, and Stephen Hawking, began to explore these solutions more deeply. They asked not just whether black holes could exist, but what they meant. Penrose, in particular, showed that singularities were not just the result of special symmetric solutions like Schwarzschild's. They were the natural outcome of collapse under broad realistic conditions. His work proved that singularities were not rare mathematical anomalies. They were unavoidable consequences of Einstein's equations under extreme density. And that realization changed everything. It meant that black holes were not optional, they were not peculiar, they were part of the structure of the universe. Where matter collapsed beyond a certain point, space-time would respond with curvature so intense that escape became impossible. The laws of physics, followed faithfully, would lead to the very edge of physics itself. John Wheeler gave them the name we still use today, black holes. Before that, they were sometimes called frozen stars or collapsed objects. But black hole captured something essential, not just the darkness, but the disappearance, the sense of falling into something with no bottom. Wheeler also helped to frame the three defining characteristics of black holes in Einstein's framework: mass, spin, and electric charge, and summarized them with the elegant phrase, "Black holes have no hair, no other features, no memories of how they formed, no trace of the structure that once made them, just these three numbers, and nothing more." This simplicity, predicted by general relativity, is both elegant and unsettling, because it means that black holes do not preserve the information of what they consume, at least not in any recognizable form. They are the ultimate erasers, the final blank slate. But the deeper physicists explored general relativity's black hole solutions, the more strange possibilities began to emerge. They found that rotating black holes described by the Kerr solution do not contain simple point singularities, but ring-shaped ones, and the space-time around them behaves in exotic ways, allowing for theoretical phenomena like frame dragging, where space-time itself is pulled around the black hole, like water swirling around a drain. Charged black holes described by the Reissner-Nordström solution added more layers, allowing for multiple horizons and complex internal structures. Solutions were found where wormholes might exist. theoretical bridges connecting distant regions of space-time, allowed by the mathematics, but unconfirmed by observation. In each case, the black hole was not just a collapse, it was a space-time geometry, a shape in the universe more extreme than anything previously imagined. And every one of those shapes came not from conjecture, but from Einstein's field equations, 10 interrelated differential equations describing how energy and momentum curve spacetime. These equations are not simple, they are deeply complex, nonlinear, and difficult to solve. Yet the black hole emerges from them naturally, a product of pure logic, of mathematical consistency, of the realization that space and time can twist upon themselves in ways that defy experience but obey law. This is the paradox at the heart of general relativity, that it gives us black holes not as inventions, but as necessities. The theory does not merely allow them, it demands them once mass is concentrated beyond a critical limit. And yet, for all its brilliance, general relativity also reveals its own boundary. At the singularity, the core of a black hole, the equations break down. They predict infinities. They predict zero volume with infinite density. They predict the end of space-time, and that prediction is not satisfying. It is a clue, a signal that something is missing, that general relativity, for all its success, is incomplete. To go further, we must bring in quantum mechanics. We must ask how particles behave at the smallest scales, how information is stored and retrieved, how entropy functions in curved space, how time behaves when gravity is not gentle but absolute. But even as we search for a deeper theory, general relativity remains our most accurate guide to the universe at large scales. It describes planets, stars, galaxies, and the grand arcs of cosmic evolution. And at its most extreme, it gives us the black hole, a silent monument to geometry, a structure made not of matter, but of space-time itself, folded so tightly that the rules of reality begin to strain. In the next chapter, we will begin to introduce the other great pillar of modern physics, quantum mechanics, and ask what happens when we bring it into the world of black hole. We will explore Hawking radiation, the strange idea that black holes are not truly black, that they can emit heat, lose mass, and eventually evaporate, because even in the darkest places, something still escapes. Chapter 8. Quantum Mechanics Meets Gravity. There is a tension that runs through modern physics, a quiet but fundamental conflict that lives at the heart of the universe. It is not a disagreement between scientists or a flaw in their logic, but a deeper contradiction, one between the two most successful theories ever developed. General relativity, which describes gravity and the fabric of space-time, and quantum mechanics, which governs the behavior of particles at the smallest scales. Both theories have passed every test. Both describe their respective realms with extraordinary precision. Yet, when we try to make them speak to each other, when we bring gravity into the quantum world, or take quantum rules and apply them to curved space-time, their voices clash, their rules break, their predictions contradict, and nowhere is that contradiction more intense than at the edge of a black hole. Black holes are where these two frameworks must meet. They are objects of enormous mass compressed into tiny volumes, where gravity is unimaginably strong, but where particles, fields, and information still try to obey the laws of quantum physics. If we want to understand what truly happens inside a black hole, not just from the outside, not just as a shape in space-time, but in the way information flows, in the way particles behave, in the way time evolves, we must find a way to make gravity and quantum mechanics speak the same language. This is not easy. General relativity treats space-time as smooth, continuous, and geometric. It bends and curves under the influence of mass and energy. But it is fundamentally classical. There is no uncertainty in its equations. Every point has a definite position. Every object follows a defined path. Quantum mechanics, by contrast, is built on probabilities. Particles are not little dots, but wave functions, clouds of possibility. They do not have definite positions until they are measured. They exist in superpositions. They entangle. They interfere. The world at the quantum scale is not deterministic. It is probabilistic, governed not by certainty, but by likelihoods. So when we ask what happens to a particle near a black hole, or what happens to light, or energy, or information, we are trying to merge two visions of the universe that were never built to be compatible. And that is exactly what Stephen Hawking did in 1974 when he asked a simple but profound question: what happens to a quantum particle at the edge of an event horizon? Using the tools of quantum field theory and curved spacetime, an approach that tries to apply quantum rules to particles while still using general relativity to describe the background. Hawking made a startling discovery. He found that black holes are not completely black. They are not perfectly silent. In fact, they emit radiation. This radiation does not come from inside the black hole. It arises just outside the event horizon, in a region where virtual particle pairs, ever present in the quantum vacuum, flicker into existence. Normally, these particle pairs appear, briefly interact, and annihilate one another, disappearing almost as quickly as they formed. But near an event horizon, something strange can happen. One particle falls into the black hole, while the other escapes. To an outside observer, it looks as though the black hole has emitted a particle, as if it has released energy, lost mass. And over time, this radiation accumulates. Slowly. Incredibly slowly. But it is real. It has a temperature. It can be calculated. And it means that black holes, contrary to what we once believed, are not eternal. They evaporate. This discovery, now known as Hawking radiation, changed everything. It bridged the gap between gravity and quantum mechanics in a way that no one had expected. It showed that black holes are thermodynamic objects. They have entropy. They have temperature. They follow the laws of thermodynamics, just like steam engines and stars and human bodies. And yet, Hawking's insight also deepened the mystery. If black holes emit radiation, and that radiation carries away energy, then over time, the black hole will shrink. Its event horizon will contract, its mass will decrease. And eventually, perhaps after trillions upon trillions of years, it will disappear completely. But what happens to the information? If a black hole forms from a complex object, a star, a planet, a cloud of gas with a unique arrangement of atoms and energy, and then evaporates away into featureless radiation, what happens to the structure that once existed? In classical physics, this is not a problem. Matter can be destroyed, patterns can be erased. But in quantum mechanics, information is sacred. The evolution of a quantum system is unitary, which means that information about its past must always be preserved in its future, even if it becomes scrambled or hidden. You cannot lose information in a quantum process, not truly, not ever. And so Hawking's result created a paradox. If black holes evaporate through a quantum process, and if that process destroys the information about what fell in, then quantum mechanics is violated. If, on the other hand, the information is preserved, then it must be hidden in the radiation somehow. But Hawking's calculation showed no trace of it. The radiation is thermal. It carries no signature. It knows nothing of the structure that created it. This is the black hole information paradox, one of the greatest unsolved problems in theoretical physics. It is not just a question of how black holes behave. It is a question of whether the laws of physics are consistent at their deepest level. It is a test of our understanding of reality itself. Since Hawking's discovery, many ideas have been proposed to resolve the paradox. Some physicists believe that information is indeed preserved, that the Hawking radiation is not truly random, but subtly encoded with the quantum fingerprints of everything that fell into the black hole. Others suggest that the event horizon is not as silent as we thought, that it stores information in a thin shell, a holographic layer, preserving the past on its surface. This view aligns with the holographic principle, the idea that all the information inside a volume of space can be encoded on its boundary. Still others propose more radical ideas, that black holes do not have traditional interiors, or that space-time itself becomes fuzzy, quantum and discontinuous at the smallest scales. Some have even suggested that information escapes in ways we do not yet understand, through wormholes, quantum teleportation, or interactions between gravity and entanglement that go beyond current theory. In each of these proposals, we see an attempt to do something very difficult, to merge general relativity and quantum mechanics into a unified picture. Because until we do, black holes will remain the great challenge, the place where our equations give contradictory answers, where our predictions become unreliable, where our confidence in the laws of physics begins to falter. But it is not a failure to admit this. It is a frontier, and frontiers are where progress begins. Quantum mechanics meets gravity in black holes not as a simple harmony, but as a dialogue between two voices speaking different languages, a dialogue that is still ongoing, still unresolved, still filled with disagreement and with hope, because in that conflict lies the possibility of something greater, a theory that unites the large and the small, a description of reality that does not break down at the singularity, or ignore the uncertainty of particles, or leave us with paradoxes we cannot resolve. A framework that will explain not just what happens at the edge of a black hole, but what lies beyond. In the next chapter we will examine one of the strangest consequences of this merger, the idea that black holes, despite being born from collapse, can evaporate. We will explore Hawking radiation more closely, not just as a calculation but as a physical reality. We will ask how black holes lose mass, what that means for their future, and whether even the most massive structures in the cosmos are destined to fade away. Because when quantum mechanics enters the world of gravity, nothing is permanent. Chapter 9. Hawking radiation. Black holes can evaporate. For most of human history, the word hole meant absence, a gap, a void, an empty space carved out of something solid. But a black hole is no such thing. It is not an emptiness. It is not a cavity floating in the cosmos. It is a region of space-time where gravity has grown so intense, so absolute, that even light cannot escape. It is dense. It is heavy. It is real, and for a long time, we believed it was permanent. Once a black hole formed, whether from the collapse of a star, the collision of dense matter, or the compaction of primordial material in the early universe, it was thought to be eternal. There was no mechanism in classical physics by which it could shrink, no known process that could remove its mass. The event horizon was a one-way surface, and anything that crossed it was forever part of the black hole's mass and fate. But in the 1970s, Stephen Hawking shattered that assumption. By carefully applying the rules of quantum field theory near the curved space-time of a black hole's event horizon, Hawking discovered something extraordinary. Black holes can emit radiation, not from inside the horizon, but from just outside it, a faint, subtle glow arising not from heat or friction, but from the vacuum itself. This radiation, now known as Hawking radiation, was not predicted by general relativity. It was born from quantum principles, the uncertainty, the fluctuations, the restlessness of empty space. In the quantum world, the vacuum is never truly empty. It is a seething ocean of temporary fluctuations, where virtual particles constantly appear and disappear in pairs, one particle and one antiparticle, borrowing energy from the vacuum for the briefest of moments before annihilating each other and vanishing without a trace. These fluctuations are normally harmless. They occur everywhere. But near an event horizon, something changes. Imagine a pair of virtual particles forming just at the edge of the black hole. In most places they would annihilate each other almost instant, but here, the immense gravity of the black hole can separate them. One particle falls into the event horizon, the other escapes into space. From the outside, it appears as though the black hole has emitted a real particle, as if something has come out of nothing. But energy cannot be created without cost. To preserve the balance, the particle that falls into the black hole must carry negative energy relative to the outside universe, and that means the black hole loses mass. Every time this happens, every time a pair is separated and one particle escapes, the black hole becomes slightly lighter. The event horizon shrinks, the total mass decreases. It is an astonishing idea. Black holes, once thought to only consume, can actually radiate. They glow faintly, coldly, invisibly to our current instruments. But they glow, and in doing so they evaporate. For most black holes, this process is slow, unimaginably slow. A stellar mass black hole, one with the mass of our Sun, would take far longer than the current age of the universe to evaporate completely. Trillions upon trillions of years would pass before it lost even a fraction of its mass. But the principle is sound, and as the black hole shrinks, the process accelerates. The smaller it gets, the hotter it becomes. The radiation increases, the evaporation speeds up. In the final stages, the black hole's temperature would rise to such extremes that it would emit not just photons, but heavier particles, electrons, muons, neutrinos, even hadrons. In the very last instant, it might release a final burst of energy, a flash of intense radiation, and then vanish completely. And what remains? That question is still unanswered. Does the black hole disappear entirely, leaving only radiation behind? Is there a remnant, a tiny stable core that never vanishes? Does the information about what fell into the black hole survive in the radiation, or is it lost forever? These are not just philosophical questions, they are central to our understanding of physics. Because if black holes evaporate, and if they truly destroy information, then something must give. Either the principles of quantum mechanics must be revised, or our understanding of gravity must evolve. Hawking's discovery did more than give black holes a temperature. It exposed a deep conflict in the foundations of modern science. Hawking radiation also changed how we think about entropy and thermodynamics. In classical physics, entropy, the measure of disorder, must always increase. The second law of thermodynamics is one of the most sacred rules in science, and black holes at first glance seem to break it. When matter falls into a black hole, its structure, its order, its complexity all disappear. From the outside, all we see is an increase in the black hole's mass. The specific configuration, the information content, the entropy of the original system, it all seems lost. That violates the second law. But in the 1970s, Jacob Bekenstein proposed that black holes themselves must have entropy, that their surface area, specifically the area of the event horizon, should be proportional to the entropy hidden within. Hawking's radiation provided the confirmation, because if black holes have temperature, and if they can emit radiation, then they must also have entropy. They are thermodynamic systems, subject to the same laws that govern steam engines and stars. The formula that emerged, the Bekenstein-Hawking entropy, tells us that the entropy of a black hole is proportional not to its volume, but to the area of its event horizon. This is profoundly strange. In everyday life, entropy scales with volume. A gas in a room has more entropy if the room is larger, but for black holes, entropy is encoded on the surface. This insight gave birth to the holographic principle, the idea that all the information in a volume of space can be described by information on its boundary. And that brings us back to the question of information loss. If a black hole evaporates completely, and if the radiation it emits is thermal, carrying no trace of what formed the black hole in the first place, then where does the information go? If it is lost, then quantum mechanics must be incomplete. If it is preserved, then the radiation must carry it somehow. But we don't know how, not yet. Some theories suggest that the information is encoded in subtle correlations within the Hawking radiation, so subtle that we have not yet figured out how to extract it. Others propose that the event horizon is not smooth and empty, but rich with quantum structure, a membrane of sorts, storing data like a cosmic hard drive. There are even more speculative ideas that the black hole connects to another universe, or that the information is preserved through entangled wormholes, or that space-time itself becomes granular at the Planck scale. Hawking himself changed his mind over time. Early in his career, he believed information was lost. Later, he conceded that it might be preserved, but that we still do not understand how. The debate continues. What is certain is this: Hawking radiation means black holes are not truly eternal. They are not perfect prisons. They do not last forever. They age, they shrink, they die. And in their death, they may teach us the ultimate truth about the universe, about how gravity and quantum mechanics coexist, about how information survives destruction, about what reality is made of at its most fundamental level. For now, we watch and wait. Hawking radiation has not yet been directly observed. The radiation is too faint, the process too slow for current technology to detect, but the theory is compelling. The mathematics is sound. And in the cold darkness of the far future, long after the stars have gone out, when the last embers of the universe are black holes quietly fading away, the truth of this radiation may finally be revealed. In the next chapter, we will explore how black holes, despite having no surface, still obey thermodynamic laws. We will look deeper at entropy, temperature, and the paradox of storing information on a surface. Because the horizon may not just be a boundary, it may be the universe's most mysterious memory.
Chapter 10: Black Hole Thermodynamics. At first glance, the very idea seems absurd. How can a black hole, an object that emits no light, that traps everything behind an invisible boundary, that has no surface, no texture, no atmosphere, obey the laws of thermodynamics? How can something so silent, so final, so removed from the familiar processes of heat and energy exchange, follow the same principles that govern fire, steam, and entropy? And yet it does. In one of the most astonishing developments in modern theoretical physics, black holes have been found to obey a set of laws almost identical to the laws of thermodynamics. This discovery did not come from observation, but from deep theoretical insight, from asking what happens to matter and energy as they fall into a black hole, and from noticing that even in this most extreme environment, certain patterns continue to hold. To understand this connection, we must first recall what the laws of thermodynamics are. These are not arbitrary human inventions. They are among the most fundamental rules in all of science, universal constraints on how energy moves, how systems evolve, and how order becomes disorder over time. The first law of thermodynamics is the law of energy conservation. It states that energy cannot be created or destroyed. It can only change forms. Whether energy appears as heat, light, motion, or chemical potential, the total amount remains the same. The second law of thermodynamics tells us that entropy, a measure of disorder or the number of microscopic configurations a system can have, always increases in a closed system. You can turn order into chaos, but not the other way around. Spilled water does not spontaneously gather itself back into a glass. Heat flows from hot to cold, not the reverse. This law is the reason time appears to move in one direction. The third law states that as a system approaches absolute zero temperature, its entropy approaches a minimum, often zero. No matter how cold something gets, there's always a limit to how much order can be achieved. Finally, the zeroth law, though named last, defines what we mean by temperature. If two systems are in thermal equilibrium with a third, they are in thermal equilibrium with each other. This establishes the basis for thermodynamic temperature as a consistent concept. Now let's apply this thinking not to a furnace or an engine or a cup of hot coffee, but to a black hole. In the early 1970s, physicist Jacob Bekenstein made a daring proposal. He noticed that when matter falls into a black hole, its information, its structure, its entropy, appears to vanish from the outside universe. This seemed to violate the second law of thermodynamics. If entropy disappears, the total disorder in the universe decreases, and that is not supposed to happen. To resolve this, Bekenstein suggested that black holes themselves must have entropy, that the increase in the black hole's mass and size must reflect an increase in entropy, hidden from the external world, but still present. He proposed that the entropy of a black hole is proportional to the surface area of its event horizon, not the volume inside, but the area around it. This idea was radical, but it became even more compelling when Stephen Hawking discovered that black holes emit radiation and therefore have a temperature. If a black hole emits radiation, then it must be losing energy. If it loses energy, it must cool down or change in some predictable way. And if it has a temperature, then it must also have entropy. Suddenly, all the pieces fit. The surface area of the event horizon plays the role of entropy. The mass energy of the black hole corresponds to internal energy. The surface gravity, the strength of the gravitational pull at the horizon, corresponds to temperature. And the changes in these quantities follow rules that mirror the laws of thermodynamics exactly. This realization led to what we now call the 4 laws of black hole thermodynamics. The 0th law states that the surface gravity of a stationary black hole is constant across its event horizon. Just as temperature is constant in a system at thermal equilibrium, so too is the gravitational temperature across the horizon of a quiet, stable black hole. The first law relates changes in the black hole's mass to changes in its area, angular momentum, and electric charge. In simplified form, it resembles the energy conservation law, accounting for how black holes respond to small perturbations, like matter falling in or energy being added. The second law, known as the area theorem, was proved by Hawking using general relativity. It states that the total surface area of event horizons in a closed system can never decrease. This mirrors the second law of thermodynamics, where total entropy must increase or remain constant. And the third law asserts that it is impossible to reduce the surface gravity of a black hole to 0 through any physical process, meaning you cannot reach absolute zero, just as you cannot for any thermodynamic system. These parallels are not coincidences. They suggest that black holes are thermodynamic objects, despite their extreme nature, despite their apparent simplicity, despite the fact that we cannot observe their interiors directly. But there is one crucial difference. In ordinary thermodynamics, entropy scales with volume. The larger a system, the more possible configurations it has, and therefore the higher its entropy. But with black holes, entropy scales with area. This is more than a mathematical curiosity. It is a clue, a profound hint, that the information content of a region of space may not be proportional to how much space it occupies, but rather to the surface that surrounds it. This insight gave rise to the holographic principle, the idea that the universe may in some deep way be like a hologram, that everything we experience in 3 dimensions could be encoded on a 2-dimensional boundary, that space and time themselves may emerge from something more fundamental, more abstract, and more deeply tied to information than we ever imagined. The fact that black holes obey thermodynamic laws, that they radiate, that they shrink, that they hold entropy on their surfaces, forces us to ask unsettling questions about the nature of reality. What is entropy? Really, what does it mean to say that a black hole has information? Can that information be retrieved? And if so, where is it stored? If the entropy of a black hole reflects the number of quantum microstates hidden behind the horizon, then those microstates must somehow describe everything the black hole has swallowed. Every atom, every photon, every moment of history that crossed its boundary. But if we cannot see them, if we cannot interact with them, if they are encoded in ways we do not yet understand, then how can we ever claim to know they exist? This is the frontier that modern physics now faces, a place where gravity, thermodynamics, quantum theory, and information science collide. A place where equations that once described engines and heat baths now whisper secrets about the most extreme objects in the universe. A place where the boundary of a black hole becomes a kind of screen, not just a horizon, but a record. In the chapters ahead, we will explore these questions further, following the threads of entropy and information deeper into the geometry of space, into the structure of black holes, and into the paradoxes that have challenged the greatest minds of our time. Because if black holes truly remember everything that falls into them, then nothing is ever really lost. And if they forget, then something in our universe is broken.
Chapter 11. Time near a black hole. Among the many strange consequences of gravity, perhaps none is more unsettling, more quietly disorienting than its effect on time. We grow up thinking of time as a constant, a fixed rhythm, universal and reliable, ticking away in the background of every moment. We assume that seconds pass the same way for everyone, that time flows forward at a steady pace, unchanging, absolute. But gravity, as described by Einstein's general theory of relativity, tells us otherwise. It tells us that time is not separate from space, but part of it. That time, like distance or direction, can be stretched, compressed, and distorted. And nowhere is this distortion more extreme, more undeniable, more permanent than near a black hole. To understand how time behaves near a black hole, we must first remember that gravity is not a force in the Newtonian sense, not an invisible hand pulling on objects across space. It is the curvature of space-time itself. Massive objects do not reach out and tug. They bend the stage on which all motion occurs. And as they bend space, they also bend time. They make it run slower in their presence, not because of any physical resistance, but because that's what curved geometry demands. This is not just theory. It has been measured. On Earth, time runs slightly slower at sea level than it does on a mountaintop. Atomic clocks placed just a few feet apart will tick at different rates if one is closer to the center of gravity. The difference is minuscule, nanoseconds or less. But it is real, and it has been confirmed to extraordinary precision. Our GPS satellites must account for these time distortions every moment they operate, or they would quickly drift out of sync with Earth-bound systems. Now take that same effect, that gentle warping of time caused by Earth's gravity, and magnify it beyond all proportion. Take it to a place where gravity is no longer a quiet curve, but a steep funnel. Take it to the edge of a black hole. Near a black hole, time does not just slow down, it stretches, it distorts. It begins to behave in ways that challenge the very meaning of the word. Imagine floating safely outside the event horizon, just far enough to remain stable, just close enough to feel the pull. You set your clock. You watch the second hand tick forward. From your own perspective, everything feels normal. Time flows as it always has, 1 second per second. But if you look out toward the stars, toward distant galaxies and the rest of the universe, you will see something strange. Their clocks are racing. Their seconds pass faster. Their years arrive in what feels like your moment. And to them, to observers far away from the black hole, it is you who appears frozen. If they could see your clock, they would see it ticking more and more slowly as you approach the black hole. If you fall closer, the discrepancy becomes more dramatic. Minutes for you become hours for them. Hours become days. Near the event horizon, the difference grows so extreme that from the distant universe's perspective, you seem to stop moving entirely. You hover, you fade, you never quite cross the line. This phenomenon is not an illusion. It is a direct consequence of the geometry of space-time. The closer you are to a massive object, the more time slows relative to observers farther away. And at the event horizon of a black hole, that slowdown becomes infinite. From the outside, nothing ever crosses the horizon. It only asymptotically approaches it, growing dimmer, redder, and slower disappears entirely. But from your own point of view, the falling observer, there is no such drama. You cross the horizon in finite time. You do not feel anything unusual. Your heart continues to beat. Your thoughts unfold. Your seconds still pass like they always have. Time for you remains smooth and continuous until you reach the singularity. This duality, this split in experience, is one of the most haunting aspects of black holes. It means that time is not universal. It is personal. It is dependent on where you are, how fast you are moving, and how deeply you are embedded in a gravitational well. The idea that everyone shares a single cosmic clock, a master timeline ticking across the universe, is an illusion. There are as many clocks as there are paths through space-time. Each object, each person, each light beam carries its own measure of time. Near a black hole, these differences become stark. If you could hover near the event horizon for an hour and then return to Earth, you would find that centuries, even millennia, had passed. You would be a traveler into the future, not by speed but by gravity. The black hole would have slowed your time so dramatically that when you emerged, the world you knew would be gone. Civilizations would have risen and fallen. Stars would have shifted in the sky. History would have flowed past you while you sat in silence, just beyond the edge. And this effect is not just theoretical. It is calculable. It is baked into the equations of general relativity. We can write down the metric, the mathematical description of space-time near a black hole, and from it derive exactly how time slows, how space curves, how light bends. We know that the gravitational redshift, the stretching of light as it climbs out of a gravity well, becomes infinite at the horizon. We know that the coordinate time, the time seen by a distant observer, diverges. We know that inside the horizon, time and space trade roles. The inward direction becomes the future. You are not just falling into a place. You are falling into a moment, one you cannot escape. This raises deep questions about causality, about determinism, about what it means for an event to happen. In the rest of the universe, time flows in one direction because entropy increases. We see causes before effects. We remember the past, not the future. But near a black hole, these assumptions begin to blur. When every path leads inward, when every direction points toward the singularity, does it still make sense to speak of before and after, or is there only toward? Some physicists believe that time at its core is emergent, not a fundamental property of the universe, but a byproduct of relationships between states. If that is true, then black holes may hold the key to understanding time itself. They may be the places where time is most malleable, most broken, most revelatory. Others suggest that time is still fundamental, that the distortions we see are not illusions, but genuine features of the universe's architecture. In this view, black holes are clocks of a different kind, not ticking hands on a dial, but gravitational wells that reshape the very rhythm of reality. Whichever view proves correct, one truth remains. Black holes are not just regions of intense gravity. They are machines that sculpt time. They are engines that rewrite the tempo of the universe, and in doing so, they reveal that time, the most familiar, most personal dimension we know, is also the most fragile, the most flexible, the most misunderstood. In the next chapter, we will explore whether a person or a probe could survive entry into a black hole. We will examine the physical consequences of spaghettification, the tidal forces that destroy, and the theoretical scenarios in which something or someone might make it past the horizon intact, at least for a while. Because once you understand how time works near a black hole, the next question becomes, how long do you have?
Chapter 12. Could you survive entry? To fall into a black hole is to fall through a boundary where the rules change. It is to cross a line that no signal can ever recross.
to enter a region where every path, every direction, every possibility leads inward towards something no theory fully explains. But if you were there, drifting just beyond the event horizon, surrounded by the quiet curves of warped space-time, the question would not be theoretical. It would be personal. Could you survive? Would you feel anything? Would you have time to think, to breathe, to understand what was happening before the end? The answer, like much in black hole physics, depends on which black hole you are falling into. Black holes come in many sizes. Some are only a few times the mass of our Sun. These are called stellar mass black holes, formed from the collapse of massive stars. Others are far more massive, tens of thousands to millions, or even billions of solar masses, lurking in the hearts of galaxies. These are called supermassive black holes, and between these extremes there may exist intermediate black holes, their origins still uncertain, their existence supported by only the faintest observational hints. Why does size matter? Because it determines the gradient of gravity, how rapidly it increases as you approach the center. This gradient, the tidal force, is what stretches you. The smaller the black hole, the more abruptly gravity changes near the event horizon. For a small black hole, the difference in gravitational pull between your head and your feet becomes enormous within meters. The result is immediate, catastrophic spaghettification. You would be torn apart by tidal forces long before you reach the singularity, possibly even before you cross the event horizon. But for a larger black hole, especially a supermassive one, the gradient is gentle. The event horizon is much farther from the singularity, and the change in gravity across your body may be negligible at first. You might cross the event horizon without noticing. No sudden stretching, no jolt, no rupture of bone or tissue, just continued free fall, silent, smooth. In that case, yes, you could survive the initial entry. You would not die at the edge. You would drift through the horizon without a sound, without resistance, without any clear sign that you had passed a point of no return. But survival is relative, because even if you are not destroyed at the horizon, your fate is already sealed. You are inside a region where escape is impossible, where time and space conspire to carry you inevitably toward the singularity. No force, no engine, no intervention from the outside can help. Your trajectory has no exit. Your journey has only one destination. Still, from your own point of view, there is time. You may have minutes, maybe hours. The exact duration depends on the size and rotation of the black hole. Inside a stellar mass black hole, your remaining time might be seconds. Inside a supermassive one, perhaps longer. But whatever the number, the question remains, what happens during that time? Could you send a message? Could you record what you see? Could you explore? In principle, yes, but only for yourself. Any signal you send outward will be redshifted into oblivion. No light escapes, no radio waves carry your story. You are causally disconnected from the rest of the universe. You could record data, but no one outside will ever receive it. You could observe, but you would never report. Even so, the environment inside a black hole is not necessarily chaotic. In the simplest models, especially for large, non-rotating black holes, the interior spacetime is still well behaved up to a point. The equations still make sense. You could, in theory, move, calculate, think. The space around you may look strange, curved, even surreal, but it would still have structure. You might see the universe behind you compressed into a small, bright patch of sky, all of history funneled into a cone of light. You might see strange gravitational lensing effects, distortions of shapes and shadows unlike anything outside. You might even look ahead, though ahead would mean deeper now, inward in a way no compass can capture. What you wouldn't see is the singularity. Not yet. The singularity is not a place in space. It is a moment in your future. Just as you cannot see next week, you cannot see the singularity from a distance. You are falling toward it in time, not in space. It is the next chapter of your experience, one you cannot skip or delay. Eventually, the tidal forces grow. Even in a supermassive black hole, you cannot descend forever without feeling their effects. At some point, gravity pulls harder on one part of you than another. The curvature sharpens. The equations begin to lose coherence. Your structure, physical, molecular, atomic, begins to unravel. Could you ever resist this? No known material can withstand the conditions near the singularity. No armor, no ship, no technology can prevent the breakdown of matter under such extreme. The very atoms that make you would be crushed. The distinctions between parts of you, head and foot, hand and heart, would dissolve. You would become a thread of mass energy following a path into mystery. But let us ask a deeper version of the question. If your body is destroyed, does that mean you are destroyed? That depends on what you believe you are. If you are your molecules, then yes, those are gone. If you are your thoughts, your memories, your pattern of information, then perhaps the story is not so final. Some theories suggest that the information you carry, the unique arrangement of particles, the structure of your experience, is not erased, but somehow encoded in the gravitational field, or in the quantum state of the horizon, or in the radiation that slowly leaks away. These are open questions, speculative, debated, rich with possibilities. Perhaps in some future theory of quantum gravity, we will learn that falling into a black hole is not the end of meaning, only the end of form. Perhaps consciousness, identity, memory, the essence of information, is more resilient than structure. Perhaps the universe remembers more than we think, but in our current understanding, survival inside a black hole is temporary. You can enter, you can observe, you can exist for a time, but you cannot escape, and eventually you cannot endure. Still, even this limited form of survival is remarkable, because it tells us that the black hole is not a wall of death at its edge. It is a funnel, a slope, a curve into the deepest part of reality. The crossing is not a termination, it is a transformation, gradual, quiet, irreversible, and in that crossing, you become part of the black hole's future. You add to its mass, you contribute to its entropy, you change its spin, its geometry, its eventual fate. You are no longer a separate observer, you are inside. In the next chapter, we will explore an even stranger possibility, that what lies inside a black hole is not a crushing end, but an exit. That according to certain solutions in general relativity, the singularity might lead not to destruction, but to emergence, into a different part of the universe, or perhaps into an entirely new one. Because where gravity bends time to a halt, it may also open a door.
Chapter 13. White holes times reverse flow. In the language of physics, every process has a mirror. Every action, if the laws are symmetrical, has a reaction. Every equation, if it respects time reversal symmetry, can run forward or backward. This symmetry under time is a deep feature of many physical laws, from classical mechanics to quantum interactions, and it invites a question we rarely consider. If something can fall in, could something fall out? If gravity can trap, can it also reject? If a black hole exists as a region where nothing escapes, could its opposite also exist? A region where nothing enters. This is the idea of the white hole. Mathematically, a white hole is the time reverse of a black hole. It is a solution to the equations of general relativity that describes not a region of space-time where things are drawn in, but one where they are pushed out violently, absolutely, permanently. A white hole is a region that cannot be entered from the outside. It explodes matter and energy outward, but cannot receive anything in return. It is not a sink, but a source. Not a prison, but a fountain. In theory,
White holes emerge naturally from the equations that describe black holes. Just as the Schwarzschild solution includes a singularity and an event horizon, it also includes a mathematical mirror, a region that is the reverse in time. In this mirror, instead of matter collapsing inward toward a singularity, it expands outward from one. Instead of events converging to a final point, they diverge from an initial one. Instead of time narrowing, it blossoms. But this mirror, while elegant in mathematics, is troubling in physics. Because we have never observed a white hole, we have never seen an object that emits matter and cannot receive it. We have never found a region of space where time appears to flow backward, where particles are expelled for no reason, where gravity repels rather than attracts. So is the white hole real, or is it a mathematical ghost? A shadow of the symmetry we see in equations, but not in nature. Some physicists believe that white holes are not physically realizable, that they are artifacts of idealized solutions, like frictionless surfaces or infinite planes. They argue that the universe, though governed by symmetric laws, is full of asymmetries in practice. Entropy increases, stars burn, arrows fly forward. Time, though reversible on paper, flows only one way in reality. But others suggest that white holes may be more than just curiosity, that under the right conditions, perhaps at the beginning of the universe, or at the end of a black hole's life, they might appear, however briefly. Some models of quantum gravity propose that when a black hole evaporates completely, its final stage may resemble a white hole, a sudden release of the information and energy it once trapped. Instead of disappearing into silence, the black hole might end with an outburst, a final exhalation, a flash of existence, a white hole born from blackness. In these models, the singularity at the heart of the black hole is not a point of termination, but a point of transformation. The matter that falls in does not vanish. It waits. It compresses. It reaches a minimum length, perhaps a Planck scale core, perhaps a region governed by loop quantum gravity, or strings or space-time foam, and then rebounds. The collapse reverses. The fall becomes a rise. The black hole becomes a white hole. This is not just poetic inversion. It is a real attempt to preserve the laws of physics, especially the law that says information must not be lost. If black holes are final, then information disappears. But if black holes turn into white holes, then the information may re-emerge, scrambled but preserved, like heat escaping from a dying fire. Such a process would take time, unimaginable time. Hawking radiation is slow. A black hole the mass of our sun would take more than 10⁶ years to evaporate. A supermassive black hole might take 10 centuries or more. But eventually, if evaporation is complete, the bounce may come. And in that moment, the universe might remember what it once forgot. Some cosmologists have gone even further. They propose that our universe itself may have originated from a white hole, that the Big Bang was not the birth of everything from nothing, but the explosion of matter and energy from a prior singularity. In these big bounce models, the universe did not begin with a singularity at time zero. It emerged from a contracting phase, a previous cosmos that collapsed, rebounded, and expanded anew. The white hole, in this view, is not just a theoretical opposite of the black hole. It is the beginning of time as we know it. Others suggest that white holes might exist in parallel to black holes, connected through wormholes or Einstein-Rosen bridges, as solutions in general relativity. In these models, what falls into a black hole in one region of space might emerge from a white hole somewhere else. The singularity is not a dead end, but a passage, a tunnel through space-time. These wormholes, if stable, could connect distant parts of the universe, or even different universes entirely. But stability is the problem. According to most classical models, wormholes are unstable. They collapse too quickly for anything to pass through. They require exotic matter, material with negative energy density, to remain open. And we do not yet know whether such matter exists in the necessary forms or quantities. Still, the mathematics invites us to imagine. It tells us that the black hole is not alone. It has a mirror, and that mirror is the white hole. What would it look like? We do not know. A white hole, if it existed, would appear as a sudden explosion of matter and energy, with no apparent source. It would be like watching a film of a black hole in reverse. Particles would fly outward from a point, collapsing, defying gravity, repelling all attempts to approach. It would be unstable, perhaps short-lived, perhaps impossible to detect before it fades. But the concept remains powerful, not because it is confirmed, but because it suggests that even in the darkest regions of space, the universe may still be playing by deeper rules. Rules that include reversibility, rules that preserve information, rules that hint at balance. White holes challenge us not with data, but with possibility. They ask us to consider that gravity, like light, may have a dual nature, that collapse may lead not to silence, but to emergence, that an end may be the beginning of something else. In the chapters ahead, we will follow this thread deeper into speculation. We will look at wormholes, at the possibility of traversable paths through space-time, and at the strange and beautiful geometries that arise when mass curves reality in more than one direction. Because the black hole may not just be a destination, it may also be a gate.
Chapter 14. Are wormholes hidden inside? There are ideas in physics that live at the border between imagination and mathematics. Ideas that begin as thought experiments, simple what-ifs, and then under the weight of geometry and logic begin to take shape. Wormholes are one of those ideas, not because we have seen one, or built one, or mapped its interior, but because the equations of general relativity whisper that such things are possible. Not easy, not stable, but possible, under the right conditions, and perhaps hidden inside the most extreme structures the universe has to offer. Wormholes, as they are popularly imagined, are tunnels through space-time, shortcuts that connect distant locations, perhaps light years apart, through a curved corridor outside normal space. But in physics, they are more precisely known as Einstein-Rosen bridges, named after Albert Einstein and Nathan Rosen, who first described the mathematical structure of such a connection. Their solution arose from the same equations that describe black holes, the Schwarzschild solution, but viewed with a twist, a reinterpretation of the singularity not as a point of termination, but as a junction between two separate regions of space-time. In the Einstein-Rosen picture, what we call a black hole could theoretically be connected to a mirror structure, a white hole, in another region of space, or even another universe. The black hole draws matter in, the white hole expels it. The two are linked by a narrow throat, a bridge of warped space-time. From the outside, the black hole looks as it always does, a dark sphere with a silent horizon. But inside, if the geometry holds, there could be a passage. This is the wormhole, a link between two mouths, each surrounded by its own event horizon, each marking a boundary in space, time, and causality. The idea is haunting. It suggests that falling into a black hole might not be a one-way trip to destruction, but a journey through a tunnel, that somewhere on the other side, you could emerge, perhaps far away, perhaps elsewhere, perhaps into a universe entirely different from the one you left behind. It turns the black hole from a grave into a gate. But before we get carried away, we must ask, does the wormhole stay open? The mathematics says, not easily. Most wormhole solutions, when analyzed closely, reveal a fatal instability. The tunnel collapses too quickly. The curvature grows too steep. The walls of space-time crush inward. Any attempt to pass through would be stopped by a singularity or shredded by tidal forces. The bridge pinches off before it can be used.
In fact, the original Einstein-Rosen bridge was not traversable at all. It existed only for an instant. The two mouths were connected in theory, but nothing, not even light, could cross the throat. The wormhole was a feature of the equations, but not a physical path. So what would it take to keep a wormhole open? This is where the discussion turns strange, because to prevent a wormhole from collapsing, you need something that violates the known energy conditions of general relativity. Specifically, you need what physicists call exotic matter, material with negative energy density, not just unusual matter or antimatter, but something that creates gravitational repulsion, something that pushes space apart rather than pulling it together. This is not the kind of matter we find in stars or planets. It is not the kind of energy that fuels engines or burns in fusion. It is something we have never directly observed, but which may not be impossible. Certain quantum fields, under very specific conditions, can exhibit negative energy density. The Casimir effect, for instance, a phenomenon observed in quantum electrodynamics, shows that vacuum energy can behave oddly between conducting plates. It hints that the vacuum is not empty and that negative energy, however brief, can exist. If such exotic matter could be harnessed, stabilized, controlled, shaped, then in theory, a traversable wormhole could be built. A throat could be held open. A tunnel could be protected from collapse. And in that tunnel, a traveler could pass. But we are far from knowing whether this is truly possible. The requirements are extreme. The engineering is unimaginable. The stability is uncertain. And the dangers, causality violations, time paradoxes, feedback loops, are profound. Some models suggest that wormholes could enable faster than light travel. Others hint that they could be used to travel backward in time. These ideas, while fascinating, bring with them problems that strike at the heart of physics, problems that threaten the very consistency of the universe. Still, even if we cannot build a wormhole, we can ask, could a black hole, under the right circumstances, contain a wormhole within it, not built by intelligence, but formed by the universe itself? Some theories say yes. Certain rotating black hole solutions, like the Kerr metric, include regions where, mathematically, a wormhole exists at the core. These structures are complex, unstable, wrapped in ergospheres and surrounded by horizons. But they show that the equations allow for internal bridges, even if they may not survive long enough to be used. Other speculative models, especially those involving loop quantum gravity or string theory, propose that black holes may be topologically complex, that their interiors may include tunnels or folds or dimensional extensions beyond our current understanding. In these models, what looks like a singularity from afar might actually be a junction point, a place where space-time folds back on itself or connects to a different region altogether. In some versions, wormholes are not just theoretical options. They are inevitable consequences of deeper principles. They arise not as exceptions, but as features of a quantum gravitational fabric that is inherently connected, networked, woven. In such a view, the universe is not smooth, but laced with microscopic tunnels. Most are too small to use. Some may be unstable, but perhaps, in the heart of a black hole, one could grow large enough to matter. Still, the observational evidence is lacking. No wormhole has ever been seen. No star has ever vanished from one part of the sky and appeared in another. No radiation has emerged from a white hole's mouth. No traveler has returned to tell the tale. These structures remain hidden, if they exist at all. And yet, the possibility remains. The equations permit it. The theories allow it. The universe has not said no, not yet. If wormholes do exist inside black holes, they would change our understanding of what black holes are. They would no longer be the final chapter in the story of collapse. They would be portals, passages, places where information is not lost, but transported, where endings become beginnings. Perhaps this is why black holes remain so compelling. not because of what we know, but because of what we do not. In the next chapter, we will return to the surface, to the event horizon, and confront one of the most heated debates in modern physics, the firewall paradox. A question that challenges the very idea of smooth space-time and asks whether the horizon itself might be far more violent than we ever imagined, because sometimes the strangest danger is not what lies inside, but what waits just at the edge. Chapter 15: The Firewall Paradox. For nearly a century, physicists believed that if you fell into a black hole, you would pass through the event horizon without feeling anything unusual. The curvature of space-time would be steep, yes, and the gravitational field intense, but the horizon itself, that invisible boundary between escape and imprisonment, was not supposed to be a place of violence. It was just a coordinate threshold, a marker in space-time. According to Einstein's general relativity, if you were falling freely, you would not notice the horizon at all. You would pass it smoothly, silently, and continue your descent inward until you reached the singularity. But quantum mechanics tells a more complicated story, and when you combine the laws of quantum physics with what we know about black hole entropy, information, and evaporation, something strange emerges, something that seems to violate either our understanding of gravity or our understanding of reality itself. This is the firewall paradox. The firewall paradox begins with a deep question: what happens to information that falls into a black hole? As we've seen, quantum mechanics demands that information must be preserved. Every physical process, even if it scrambles information into unreadable form, must be unitary. That means the total information content of the universe cannot decrease. So if a black hole forms from matter that contains information, atoms, structures, thoughts, data, and that black hole later evaporates via Hawking radiation, then somehow that information must be encoded in the radiation, otherwise quantum mechanics breaks. This idea leads to the concept of black hole complementarity, the theory that information is both reflected at the horizon for outside observers and passes through for infalling observers, but never both at the same time for any single observer. It is a clever resolution, one that tries to preserve both general relativity and quantum mechanics. It says that no observer ever sees a contradiction, because no observer can be both inside and outside the black hole. What is true for the falling observer can differ from what is true for the observer at a distance, and as long as those two experiences cannot be compared, there is no paradox. But in 2012, a group of physicists, Ahmed Amheri, Donald Maroff, Joseph Polchinski, and James Sully, challenged this idea in a now famous paper that became known as the AMPS paradox, or simply the firewall argument. They showed that under the assumptions of black hole complementarity, unitarity of quantum mechanics, and the validity of quantum field theory near the horizon, you reach a contradiction. You cannot have all three. One must break. Their argument goes like this: if the Hawking radiation emitted by the black hole carries information, then each outgoing particle must be entangled with earlier radiation. That is how information escapes. But the same particle, according to quantum field theory, should also be entangled with its partner particle just inside the horizon, a requirement for the vacuum state to be smooth and for the falling observer to experience nothing unusual. But quantum entanglement does not work this way. A quantum system cannot be maximally entangled with two different systems at the same time. This is known as the monogamy of entanglement. So if the outgoing particle is entangled with past radiation, to preserve unitarity, it cannot also be entangled with its partner inside the horizon. Something has to give. And if the entanglement with the interior particle is broken, then the smooth vacuum state at the horizon is destroyed. Instead of falling gently through the horizon, the infalling observer would encounter high-energy particles, a searing wall of radiation, what the AMPS authors called a firewall. This firewall would not be visible from the outside. It would not shine. It would not emit light. but it would exist just at the event horizon, a discontinuity in space-time, a violation of Einstein's equivalence principle, a place where the geometry itself becomes violent. In other words, if the Amps paradox is correct, then falling into a black hole would not be peaceful. It would be lethal, not at the singularity, but at the horizon itself. This idea shocked the physics community. For decades, it had been accepted that the event horizon was smooth, that general relativity could be trusted at that boundary. The equivalence principle, one of the cornerstones of Einstein's theory, says that locally, in free fall, you should not be able to distinguish between gravity and acceleration. It says that if you are floating near the horizon of a black hole, you should feel weightless, not incinerated. But the firewall argument says otherwise. It says that our understanding of space-time is incomplete, that to preserve quantum unitarity, to ensure that information is not lost, we may need to sacrifice the smoothness of space, that the horizon is not empty, but hot, not silent but violent. This presents a crisis. If firewalls exist, then general relativity fails at the horizon. If they do not exist, then unitarity might fail, or our understanding of entanglement must change. The Amps paradox forces us to confront the uncomfortable reality that our two greatest theories, general relativity and quantum mechanics, are in tension, not just at the singularity, but at the very surface of the black hole. In the years since the paradox was proposed, many resolutions have been suggested. Some theorists argue that subtle correlations in the radiation can preserve unitarity without breaking the entanglement with interior partners. Others invoke holographic principles, saying that the horizon encodes information in a way that avoids the paradox entirely. Still others suggest that the concept of space-time itself must be revised, that the geometry we trust is emergent, approximate, and breaks down near horizon. A few physicists have even embraced the firewall, saying that our loyalty to smooth horizons is misplaced, that perhaps firewalls are real, and the equivalence principle, though beautiful, is not absolute. But no consensus has emerged. The paradox remains unresolved. The firewall stands, not as a physical wall confirmed by experiment, but as a warning that somewhere, in the space between relativity and quantum mechanics, lies a contradiction we do not yet understand. And this contradiction is not small. It lives at the boundary between causality and chaos. It questions whether space is continuous. It asks whether information can fall in and still come out. It challenges whether the universe itself plays by consistent rules, or whether at its edges, reality begins to fracture. If firewalls exist, then the black hole is no longer a one-way gate into silence. It is a searing wall, a quantum rupture in the fabric of space-time. If they do not exist, then we must explain how information escapes without violating entanglement, unitarity, or geometry. Either way, something must change. In the next chapter we will leave the horizon behind and look deeper into the puzzle of information itself. We will ask what it means to say that a black hole remembers, and how, if at all, that memory might return. Because if firewalls threaten to burn everything at the surface, the deeper mystery remains. Where does the information go?
Chapter 16: Information Paradox. Does anything ever escape? There is a truth we have trusted for over a century, that information in the quantum world cannot be destroyed. You can scatter it. You can hide it. You can entangle it, scramble it, bury it inside a cloud of probabilities. But you cannot make it vanish. This rule, known as unitarity, is not just a feature of quantum theory. It is its foundation. The evolution of quantum systems is deterministic, not in the classical sense of predictable outcomes, but in the deeper sense that every state evolves into another, preserving the total content of information. And yet, black holes appear to violate this. They consume matter. They trap light. They absorb everything that crosses the horizon. Particles, photons, quantum states. And then,
Over billions of years, they radiate away that mass in the form of Hawking radiation, a gentle, slow leak of thermal particles, seemingly devoid of memory. That radiation, first proposed by Stephen Hawking in the 1970s, is not entirely speculative. It emerges from combining quantum mechanics with curved space-time near the event horizon. Pairs of virtual particles form near the horizon. One falls in, one escapes, and the result is a slow evaporation of the black hole itself. This process, according to Hawking's original calculation, is purely thermal. It carries energy but no information. It is noise, not signal. Blank, featureless radiation, indistinguishable no matter what the black hole was made from. And this is where the information paradox begins. If a black hole evaporates into nothing but thermal radiation, and that radiation carries no imprint of the matter that formed it, then the information about the original state, the atoms, the configurations, the quantum correlations, is lost forever. This would mean that the universe has an information sink. That quantum states can end in oblivion. That unitarity, the bedrock of quantum physics, has a crack. But this conclusion is deeply troubling. It would imply that the evolution of the universe is not reversible, that a pure quantum state can become a mixed state, that something fundamental is broken, either in our understanding of black holes or in the rules we thought were absolute. For decades, this paradox simmered, unresolved. Hawking himself defended the idea that information was lost, even as others challenged it. The debate was not just theoretical, it reached into the core of physics, demanding reconciliation between quantum mechanics and gravity. Then, slowly, new ideas began to surface. Some physicists proposed that information is not truly lost, but encoded subtly in the Hawking radiation itself. That the radiation is not perfectly thermal, but contains correlations, patterns, echoes, statistical fingerprints of the information that fell in. These correlations would be imperceptible at first, but grow over time. They would emerge slowly in what became known as the Page curve, named after physicist Don Page, who argued that information must begin to leak out after a certain point in the black hole's life. According to this model, the radiation emitted early in the black hole's life is nearly random. But as the black hole shrinks, it begins to release, not just energy, but memory. The later radiation becomes increasingly entangled with earlier emissions, forming a full quantum description of the original state. If this is correct, then a black hole does not erase information. It scrambles it, delays it, and then slowly releases it back into the universe. This idea preserves unitarity, but it raises more questions than it answers. How is the information encoded in the radiation? Where is it stored while the black hole still exists? When does the leakage begin? And above all, what mechanism allows a particle emitted from near the horizon to know about the complex interior structure of the black hole, a region causally disconnected from its point of origin? To explain this, physicists turn to the holographic principle, the idea that the information content of a volume of space can be represented not inside, but on its boundary. In this view, the event horizon of a black hole acts as a kind of screen, a two-dimensional surface encoding three-dimensional information. What falls into the black hole imprints itself on the horizon, and this imprint evolves over time, influencing the outgoing radiation. This idea gained traction through the work of Gerard Hooft, Leonard Susskind, and later the ADAS-CFT correspondence, developed by Juan Maldacena, a deep mathematical duality between gravity in a higher dimensional space and a quantum field theory on its boundary. In this holographic framework, black holes become less like traps and more like processes. They take information in, transform it through complex entanglements, and eventually emit it, subtly, completely, and without contradiction. If this is true, then the paradox is resolved. The radiation is not thermal in the strictest sense. It carries structure so subtle, so entangled, so beyond our current detection, that it appears random only at first glance. But at the deepest level, the universe never forgets. Still, not everyone agrees. Some argue that if the information is truly encoded in the Hawking radiation, then the horizon cannot be smooth. That some new physics, like the firewall we discussed earlier, must intervene to preserve unitarity. Others believe that quantum gravity, still in its infancy, will reveal a deeper resolution, one that does not require sacrificing the horizon or the interior or the laws of thermodynamics. And some propose that information is not stored at the horizon at all, but in the entanglement structure of space-time itself, that the geometry of the black hole is not fixed, but built from relationships, correlations, mutual dependencies between all parts of the system, inside and out. These ideas remain speculative. No experiment has yet confirmed the encoding of information in Hawking radiation. No simulation has revealed the full dynamics of evaporation, and no probe has returned from beyond the horizon to settle the debate. But the paradox has reshaped physics. It has shown us that black holes are not just dead ends. They are testing grounds for our most fundamental ideas. They are places where gravity and quantum mechanics collide, not in chaos, but in question. They force us to ask not just what happens to matter, but what it means to know what happened. They challenge us to understand what information truly is, not just as data, but as structure, continuity, and memory. In the end, the black hole may not be a destroyer of information. It may be the universe's most extreme archivist, hiding, encrypting, distilling knowledge until it is safe to release. In the next chapter, we will explore the speculative possibilities that arise if information escapes not through radiation, but through wormholes, a radical concept known as EPR, suggesting that entangled particles might be connected by hidden bridges, and that black holes themselves may be linked through threads of quantum geometry. Because in a universe built from information, even the shortest connection may stretch across eternity. Chapter 17, EPR. Are all entangled particles connected by wormholes? In the early 20th century, physics was split by a paradox. On one side stood Albert Einstein, who believed that the universe must be local, continuous and causal, that effects must follow causes, and no information could travel faster than light. On the other side stood the emerging strangeness of quantum mechanics, where particles could become entangled, linked across space, their properties dependent on each other, no matter how far apart they were. Einstein rejected this. He called it spooky action at a distance. He insisted that such non-local behavior was impossible, that quantum mechanics must be incomplete, that there had to be hidden variables underneath. In a famous 1935 paper co-written with Boris Podolsky and Nathan Rosen, he laid out the problem. It became known as the EPR paradox, a challenge to the very heart of quantum theory. That same year, Einstein and Rosen wrote another paper. This one described a strange feature of general relativity, a bridge connecting two regions of space-time, a wormhole. In their formulation, it was a geometric solution, a tunnel through the curvature of space, connecting two black holes, or perhaps even two universes. It became known as the Einstein-Rosen bridge. For decades, these two papers were treated as entirely unrelated. One was about the foundations of quantum theory. The other was about the geometry of gravity. They belonged to separate realms, one microscopic, one cosmic. But in 2013, a radical proposal brought them together. Two physicists, Juan Maldacena and Leonard Susskind, suggested a bold equivalence, that entangled particles are connected by wormholes, that the EPR paradox and the Einstein-Rosen bridge are not just conceptually related, but physically identical. They called this idea It is one of the most audacious ideas in modern theoretical physics, and if it's true, it could be the key to unifying quantum mechanics and gravity. What does it mean? At its heart, EPR proposes that every pair of entangled particles, no matter how small, how distant or how subtle their connection, is joined by a tiny wormhole, not a tunnel we can travel through, not a bridge in the classical sense, but a fundamental link in the fabric of space-time, a thread of geometry that encodes entanglement as curvature, connection as topology. In this view, entanglement is geometry. Wherever you find two particles in a shared quantum state, you are also at a deeper, more hidden level, finding a connection in space. The wormhole is not visible. It carries no light. It may be non-traversable, like the Einstein-Rosen bridge, but it is there, written into the structure of space-time by the quantum correlations themselves. This idea is more than metaphor. In the holographic principle, especially in the Adair-CFT correspondence, there is growing evidence that entanglement creates, that the smoothness of space-time in the bulk is built from the entanglement structure on the boundary, that if you disentangle the pieces of a quantum field theory, the geometry it describes falls apart. Space itself disintegrates. EPR takes this one step further. It says that black holes formed from entangled particles are not merely correlated, they are connected. That a pair of black holes created in a shared quantum state, even if they move apart, remain joined by a hidden wormhole, and that the Hawking radiation emitted by a black hole, entangled with the interior, may itself form the other mouth of a wormhole, leading to the provocative possibility that black hole evaporation is not a loss of information, but a process of quantum teleportation across geometry. In this way, EPR offers a possible resolution to the information paradox. It suggests that the entanglement between a black hole and its Hawking radiation is not just statistical, it is physical. The information is not merely leaking out, it is traveling through microscopic wormholes encoded in the very structure of entanglement. But the implications run even deeper. If every entangled system corresponds to a geometric connection, then space-time is not fundamental, it is emergent. Space is built from entanglement. Geometry is a product of quantum relationships. In this vision, the universe is not a grid in which particles float. It is a network of connections, and space is what emerges when enough of those connections are structured in the right way. This is a profound shift. It means that quantum mechanics is not just a theory of particles, but a theory of space itself. That entanglement is not weirdness, it is architecture. It builds the world. It constructs the smoothness we walk upon, the distances we measure, the paths light takes. The more entangled a region, the more connected it is. The more correlated, the more solid. The less entangled, the more it frays. EPR also suggests that black holes, the most extreme objects in the universe, may not be special exceptions, but clear expressions of this principle, that their interiors are woven from entanglement, that their horizons are not boundaries, but veils, cloaking networks of wormholes and connections invisible to the classical eye. Could this be tested? Not yet. The wormholes of EPR are too small, too subtle, too abstract to probe with current technology. They are not traversable. They do not allow signals to pass in ways we can measure. But in theoretical models, especially in holographic simulations and toy versions of gravity, the correspondence holds. The equations match. The structure makes sense. In 2022 and beyond, physicists have begun to show that wormhole-like behavior can be simulated in quantum systems, that under certain conditions, signals can appear to pass through entangled qubits in ways that mirror traversable wormholes. These models are crude, simplified, symbolic, but they hint that EPR may be more than poetry. It may be physics. Of course, many questions remain. What exactly is the geometry of an entangled pair? How does entanglement scale into connectivity? Can wormholes ever be made traversable without violating causality? What does this mean for cosmology, for the early universe, for the very structure of time? These are the questions EREPR provokes, not with final answers, but with a bold new framework. That the universe is not built from things, but from relationships. That the void is not empty. That behind the illusion of separation, everything is quietly, invisibly, impossibly connected. In the next chapter, we will explore what happens when black holes collide, when two massive wells of space-time merge into one, distorting the geometry of the universe itself. We'll follow the waves that ripple outward from such collisions, the gravitational echoes of cataclysm, and what they reveal about the structure of space-time. Because sometimes the best way to understand what's inside is to listen to what comes out. Chapter 18. When black holes collide. The sound of space-time itself. For most of human history, the universe was silent. Not because it lacked motion, or energy, or violence, but because we could only see it with light. Our telescopes, as powerful as they became, could only observe the visible, the luminous, the electromagnetic. We watched stars burn, galaxies spin, nebulae glow. But the dark parts of the cosmos, the parts with no light to offer, remained beyond our reach. And then, in 2015, that silence broke. Not with a bang, not with a flash, but with a whisper, a signal so faint, so fleeting, that it stretched space itself. It wasn't light. It wasn't sound. It was a wave in the fabric of space-time. A ripple in gravity. A message sent over 1 billion years ago from the collision of two black holes. And we heard it. This was the first direct detection of gravitational waves, a confirmation of a prediction made by Einstein a century earlier. The experiment, known as LIGO, the Laser Interferometer Gravitational Wave Observatory, recorded a tiny change in distance, smaller than the width of a proton, caused by a passing wave of gravity. That wave had traveled across the universe, untouched, undisturbed, carrying with it the final seconds of a dance between two enormous black holes, each dozens of times more massive than our sun. When they merged, they didn't produce light. They didn't emit particles. They emitted gravity, pure, unfiltered geometry, shaking the cosmos in every direction. For the first time, we were not just seeing the universe. We were listening to it. The waveform, once translated into sound, rose and fell like a chirp, a soft tone that climbed in pitch and then vanished. It was brief, it was beautiful, and it was deeply, profoundly significant, because it told us that black holes are real, not just solutions to equations, not just theoretical constructs. They are out there spinning, colliding, merging, and in doing so, they are singing. Not in air, not in pressure waves, but in the raw movement of space itself. Their song is gravity, and now we can hear it. But how do black holes collide? It begins when two black holes orbit one another. A binary system, locked in mutual attraction. They spiral slowly inward, losing energy not through light, but through gravitational radiation. Each revolution disturbs the surrounding space-time, creating ripples that radiate outward at the speed of light. These ripples, the gravitational waves, carry away energy and angular momentum, shrinking the orbit. The black holes draw closer. The frequency of their dance increases. The spiral tightens. The waves grow louder, until finally they merge. At the moment of collision, the space-time curvature becomes extreme. The event horizons coalesce. A new black hole is born, more massive than either parent, but slightly less than their total mass combined. The missing mass is not lost. It is transformed into gravitational waves, energy flung outward in all directions, shaking the universe. These waves are not easily absorbed. They pass through matter, through gas, through stars, through galaxies. They are not scattered by dust. They are not blocked by walls. They travel vast distances unimpeded, carrying with them the full story of their origin, the masses involved, the spins, the distance, the time. And when they reach Earth, we can detect. Gravitational wave detectors like LIGO and Virgo use powerful lasers to measure tiny changes in distance caused by these waves. Two beams of light are sent down perpendicular arms, reflected by mirrors, and if a gravitational wave passes, the arms stretch and squeeze, altering the interference pattern. It is a delicate, nearly impossible measurement, but it works, and it has revealed a universe more dynamic than we imagined. Since 2015, dozens of black hole collisions have been observed. Each one tells a new story. Some involve black holes of equal mass, others are lopsided, some spin, some tumble, some merge cleanly. Others send out a kick, launching the new black hole through space. These events are not rare. They are happening all the time, all across the cosmos, but we have only now learned how to hear them. What do these collisions teach us? First, they confirm the reality of black holes as astrophysical objects. Second, they reveal their masses and distribution. Third, they test general relativity under extreme conditions, confirming again and again that Einstein's theory holds even in the most violent events imaginable. Fourth, they hint at the history of stars, because every black hole was once a massive star that died in collapse. But perhaps most fascinatingly, black hole mergers give us a glimpse into the very nature of gravity itself. Because gravitational waves are not particles, they are not fields in the traditional sense. They are oscillations in the metric waves of geometry. When we detect them, we are watching the shape of space change. We are observing not what happens inside the universe, but what happens to the universe. These waves are pure information. They encode the properties of their source, mass, spin, location, time. But they also carry mysteries. Some waveforms show anomalies, small deviations, unexpected features, subtle shifts. Could these be signs of new physics, extra dimensions, modified gravity, the imprint of quantum effects? Some theorists believe that careful study of the ring-down phase, the moments after the black holes merge, as the new black hole settles into equilibrium, may reveal the structure of the event horizon, the nature of the singularity, or even the presence of exotic matter. Others hope that future detections of black hole neutron star collisions will tell us about the equation of state of dense matter, something we still don't fully understand. And in the far future, next-generation detectors, like LISA, the Laser Interferometer Space Antenna, will orbit the Sun, searching for low-frequency waves from supermassive black hole mergers at the centers of galaxies. These events will be quieter, longer, deeper, the slow song of cosmic giants. In these signals, we will not just learn about black holes, we will learn about galaxy formation, about the growth of structure, about the past, and perhaps even the future of the cosmos. Because gravitational waves do not fade, they do not decay, they travel. They last. They are the echoes of events that once bent the entire universe. They are the closest thing we have to a memory written into the structure of reality itself. In the next chapter, we will look not at what happens when black holes meet, but at what happens when they vanish. We'll explore the strange, slow process of Hawking radiation, and what it means for a black hole to evaporate, to disappear, to die. Because even in death, the black hole still speaks. Chapter 19. How Black Holes Die. The Long Silence of Hawking Radiation. When we think of death in the universe, we imagine explosions, supernovae tearing stars apart, gamma-ray bursts slicing through space, collisions, collapses, cosmic fire. But not all endings come with sound and fury. Some are slower, colder, quieter, and among these, the most haunting of all is the death of a black hole. A black hole, by its very nature, consumes everything. It absorbs light, matter, time itself. Nothing escapes. Nothing resists. It is the universe's great eraser, and for much of history, We believed it was eternal. Once formed, a black hole would remain forever, silent, dark, unchanging. But in 1974, that assumption shattered. In a groundbreaking insight, Stephen Hawking combined the principles of quantum mechanics with the curved geometry of space-time and showed that black holes are not completely black. They emit radiation, slowly, quietly, relentlessly. This radiation is now called Hawking radiation, and it means that black holes can and will eventually die. But how can something that traps everything emit anything at all? The answer lies not inside the black hole, but just outside its boundary, at the event horizon, where quantum fields ripple in the vacuum. In quantum theory, the vacuum is never truly empty. It teems with virtual particles flickering into existence in pairs, then annihilating each other in a blur of probability. Normally, these pairs are born and die without consequence. But near the event horizon, strange things happen. Imagine a pair of virtual particles forms right at the edge of the black hole. One falls in, the other escapes. The particle that escapes becomes real, a bit of radiation drifting outward. Its partner, now swallowed by the black hole, carries negative energy relative to the outside. And because energy must be conserved, the black hole loses a tiny bit of mass. This is Hawking radiation. It is not hot. It is not fast. It is not even visible for stellar mass black hole. The temperature is inversely proportional to the mass, so the bigger the black hole, the colder its radiation. A black hole the size of a star emits less than 1 photon per year. But over time, unimaginable stretches of time, the effect accumulates. The black hole shrinks, bit by quantum bit. As it evaporates, its temperature rises. The radiation grows stronger. The decay accelerates. Eventually, after eons, the black hole becomes small enough that the radiation is no longer negligible. It begins to glow. It begins to radiate in earnest. Its mass drops rapidly. Its temperature soars. And then, in the final moments, it flares and vanishes. What remains? No one knows for sure. Perhaps nothing. Perhaps a flash of high-energy radiation. Perhaps a remnant, a stable core that can no longer radiate. Or perhaps, encoded in the outgoing radiation, is the full history of everything the black hole ever consumed. Scrambled, yes, but preserved, whispered back into the universe, through a quantum breath. But this is not something we can see. No black hole in our observable universe is old enough to have evaporated significantly. Most are still growing, fed by stars, gas, or mergers. Hawking radiation is far too faint to detect with current instruments. It remains theoretical, but not optional. It is a necessary consequence of our best understanding of quantum fields in curved space. To deny it would be to break the consistency of theory itself. So we accept it. We accept that black holes are not eternal, that even the darkest, most massive objects in the cosmos have a lifespan. That time eats even the things that eat time. But Hawking radiation does more than just erase a black hole. It touches the deepest puzzles of physics. Because, as a black hole radiates, we must ask, where does the information go? Is it destroyed? Is it preserved in the radiation? Does it bleed slowly outward? Or does it collapse into a singular quantum core, never to emerge again? These are the questions behind the black hole information paradox, questions we explored before, but which grow sharper in the light of evaporation. If a black hole dies completely, and its radiation is truly thermal, then information is lost. And that cannot be, not in quantum theory. So something must give. Perhaps the radiation carries the information, encoded in subtle correlation. Perhaps the interior is connected to the outside, through hidden geometry. Perhaps the final burst, the last quantum flare, releases a final message. Or perhaps there is no message at all, and the universe finds a way to unwrite the rules when no one is looking. But even if the information survives, we still face a haunting reality. Black holes die. Given enough time, far more than the current age of the universe, even the supermassive giants at the centers of galaxies will radiate away. The stars will die. The galaxies will fade. The universe will grow cold and empty. And in the darkness, the black holes will whisper their last. This is not just science fiction. It is the predicted future. We are living in a bright early chapter of the cosmos, a time of light and structure. But the age of black holes will come and pass, and what remains after that is unknown. Perhaps the vacuum itself will decay. Perhaps new universes will be born, or perhaps silence will settle forever. Not as an end, but as a long, slow stillness, a quiet so vast that even time forgets how to pass. In the next chapter we will ask whether the end is really the end, or whether black holes might be reborn. We'll explore the speculative world of black hole bounce models and Planck scale physics, because in the deepest voids, at the smallest scales, death and birth may be the same thing.
Chapter 20. Do black holes bounce, or is there a universe inside? For centuries, death has been seen as final, a collapse, an end. And in physics, few things feel more known ending than a black hole. When matter falls in, it disappears. When space folds in on itself, there is no going back. And when gravity becomes infinite, even time seems to stop. But what if that's not the end? What if the black hole does not mark a full stop in the universe's story, but a comma? What if something comes next? This is the radical idea behind black hole bounce models, theories that suggest that instead of ending in a singularity, a black hole might lead somewhere. That deep inside, where gravity becomes extreme and space-time curves beyond recognition, something happens. Something something new. To understand why this idea is even possible, we have to look at the singularity, the point at the center of a black hole where, according to general relativity, density becomes infinite and the equations break down. But infinities are not physical. They are signs that our theories have reached their limit. A singularity isn't an object. It's a failure to predict. And that failure may be hiding something deeper. Many physicists believe that the singularity is not real, but a placeholder, a region where quantum gravity takes over. And because we do not yet have a full theory of quantum gravity, we don't know what actually happens there. But some models suggest that the collapse does not continue forever. Instead, it reaches a minimum, a limit to compression, and then rebounds. This is called a quantum bounce. The idea comes from analogies with loop quantum gravity, a theory in which space itself is made of discrete loops, quantized units of geometry. In this framework, just as matter resists infinite compression due to quantum pressure in neutron stars, so too might space itself resist being crushed to zero. When the curvature becomes extreme enough, it pushes back. The collapse halts. A bounce occurs, but a bounce to where? One possibility is that the black hole turns into a white hole, a theoretical object that is the time reverse of a black hole. Instead of drawing matter in, it expels it. Instead of trapping everything, it releases everything. In this view, the matter that falls into a black hole does not disappear forever. It waits. It compresses. And then, one day, it re-emerges, not as evaporation, but as a burst. The time between the collapse and the bounce could be long, unimaginably long from the outside. But from the perspective of the matter inside, time may pass differently. In some models, a black hole becomes a kind of tunnel, a transition from one phase of space-time to another. What appears as a long silence from our viewpoint may be, from within, the briefest heartbeat.
And what if that tunnel doesn't just open into our universe, but into another? Here we enter the idea that every black hole may contain a universe. It's a bold hypothesis. But if space and time are allowed to curve and evolve beyond classical rules, then perhaps the interior of a black hole does not just end in a point. Perhaps it expands. Perhaps it gives rise to a new region of space-time, a budding cosmos, growing behind the veil. This would make black holes the seeds of creation. Every collapse in one universe could be the Big Bang of another. Our own universe may have begun this way, not from nothing, but from the death of a black hole in some larger parent cosmos. A cycle of universes, linked by bounces, each born from the gravitational death of the last. This idea is not just poetic. It appears in models of cosmological natural selection, in which universes that produce more black holes give rise to more offspring. Over time, the multiverse evolves, not randomly, but toward the physical constants that favor collapse and rebirth. It's a staggering possibility. In this view, a black hole is not a coffin. It is a womb. But the challenges are enormous. We do not yet know how to unify general relativity and quantum mechanics in a way that makes predictions testable. We do not know how information would be preserved across the bounce. We do not know how or whether such internal universes could be detected, even indirectly. And yet, there are clues. Some physicists suggest that the remnants of black holes, after their evaporation is complete, might leave behind signatures, perhaps small deviations in the cosmic microwave background, perhaps exotic particles, perhaps gravitational waves that don't match known mergers, perhaps statistical anomalies in entropy itself. Others look to holography, the idea that the boundary of a region encodes its entire volume, and ask whether the bounce is visible from the outside as a subtle change in the black hole's horizon structure, or in the correlations between emitted particles. Some go even further, suggesting that the Planck scale geometry inside black holes might be observable indirectly through fast radio bursts, high-energy cosmic rays, or the behavior of hypothetical particles near the end stages of black hole evaporation. But all of this remains speculative. What we do know is this: the singularity is a question mark. And wherever there is a question mark in physics, there is room for wonder. The universe may not end where we thought. It may curl back. It may tunnel through. It may rise again. And if that's true, then black holes are not just destinations. They are thresholds. They mark the edge of what we know and the beginning of what we might one day understand. In the next chapter, we will explore time itself, how it behaves near black holes, how it slows, stretches, and perhaps even breaks down. Because when gravity bends space, it also bends time. And the closer we get to the horizon, the stranger that time becomes. Chapter 21: Time Dilation Near the Event Horizon. When 1 second lasts forever, time is something we trust without thinking. It ticks, it flows, it carries us forward moment by moment. We measure it in hours, in days, in lifetimes. It feels constant, universal, immutable. But this is an illusion, because time, like space, bends. And nowhere does it bend more dramatically than near a black hole. To understand this, we have to return to Einstein's general theory of relativity. In it, gravity is not a force in the traditional sense. It is the curvature of space-time itself. Mass tells space how to curve, and space tells mass how to move. And time is not separate. It is part of the fabric. It stretches, compresses, slows, and distorts alongside space. Near any massive object, time ticks more slowly than it does far away. This effect is called gravitational time dilation, and it is not just theory, it is measurable. Even on Earth, A clock at sea level ticks slightly more slowly than a clock on a mountaintop. GPS satellites must correct for this difference to remain accurate. But near a black hole, the effect becomes extreme. As you approach the event horizon, the point of no return, time begins to stretch. Not for you if you're falling in. From your perspective, time flows as it always has. You breathe, your heart beats, you fall. But to an outside observer, watching from a safe distance, your time appears to slow. You move more sluggishly. Your signals redshift. Your voice drops in pitch. Your heartbeat fades. And just before you cross the horizon, from their point of view, you appear to freeze. You hover, never quite crossing, never quite falling in, suspended in a kind of temporal twilight. A final image, held forever. This is not a trick of light, it is the geometry of space-time itself. To the distant observer, the journey into the black hole takes an infinite amount of time. They will never see you vanish. You will never quite fade from view. But to you, the traveler, the fall is finite. You reach the horizon. You cross. You end. Time for you continues, even as the outside world accelerates into an unreachable future. This is the paradox of time near a black hole. It is relative, not in the casual sense but in the profound physical sense that time depends on where you are and how fast you're moving. There is no single universal clock. Each path through space-time carries its own rhythm, and this has consequences. It means that if you were to orbit close to a black hole safely outside the horizon, but deep within its gravitational well, you could slow your time relative to the universe. You could, in theory, spend minutes near the black hole while years pass elsewhere. You would return to a future that left you behind. This is not fiction. It is fact. Time dilation near strong gravity is real. We've observed it near neutron stars. We've calculated it near Sagittarius A, the supermassive black hole at the center of our galaxy. And one day, with more advanced technology, we might experience it firsthand. But near the event horizon, the effect grows sharper. Clocks slow to a crawl. Light stretches into red, then into radio, then into silence. Time, for the outside, approaches infinity. And if the black hole is rotating, or charged, the picture becomes even more complex. The horizon may not be a simple surface, but a layered structure. Space itself may swirl. Time may twist. The interior may contain corridors, paths, paradoxes. But the one constant remains. The flow of time is not fixed. In some models, time may even stop. Not just slow, but halt, frozen at the horizon, unreachable from within or without. In others, time may reverse, or loop, or fragment. We do not know. Our equations fail at the singularity. Our measurements cannot penetrate the veil. But this much is certain. Black holes break our intuitions about time. They show us that past and future are not fixed points, but coordinates in a flexible map, that simultaneity is an illusion, that clocks are not universal, and that at the edge of gravity's deepest well, 1 second can last forever. This is not just an abstract idea. It shapes our understanding of the universe. It affects how we model the early cosmos, where gravity was strong and space-time was curved. It influences our search for a theory of everything, one that can describe both the quantum and the cosmic. It forces us to reconsider the nature of memory, entropy, and the arrow of time itself. Because if time can slow, stretch, or stop, what does that say about beginnings, about endings, about what it means to exist in the first place? In the next chapter, we'll step even further into speculation, into the realm where black holes meet consciousness, information, and quantum paradox. We'll ask whether the universe is not just aware of black holes, but whether black holes are aware of the universe. Because when the fabric of space and time is pulled to its limits, the boundary between physics and philosophy begins to dissolve. Chapter 22. Are black holes conscious? Information, observation, and the limits of physics. It begins with a question that doesn't fit inside any equation. Can something that absorbs everything become aware of anything? To ask if black holes are conscious is to enter a strange territory, a boundary between science and philosophy, between physics and perception. At first glance, the question seems absurd. Black holes are not minds. They are not brains. They are gravitational solutions to Einstein's field equations. They are objects, not observers. And yet, they interact with information in ways no other object does. They measure in a sense. They respond. They encode. They seem to remember, but in a language we barely understand. Let's start with what we know. In classical general relativity, a black hole is defined by just three quantities: its mass, its charge, and its spin. This is the content of the no-hair theorem. The idea that black holes have no other distinguishing features. All other details about the matter that formed them, its shape, structure, history, are erased. But quantum theory complicates this picture. In quantum mechanics, information must be conserved. If you know the exact quantum state of a system, that information cannot simply vanish. And yet black holes seem to do just that. When something falls into a black hole, its information disappears from the outside world. And when the black hole eventually evaporates through Hawking radiation, that radiation appears to be random, devoid of memory. This is the heart of the black hole information paradox. Where does the information go? Is it truly lost? Is it encoded in the horizon? Is it stored in the Hawking radiation? Is it preserved through EREPR-style wormholes? Or is something deeper happening? Some physicists suggest that black holes are not just absorbers of information, they are processors, that the event horizon acts like a quantum screen, scrambling information in ways that preserve its content, but hide it behind layers of entanglement. In this view, the black hole is not a passive sink, but an active participant in the evolution of the system. Still others propose that black holes behave like quantum computers, taking inputs, applying transformations, and emitting outputs that, while seemingly random, contain structured correlations. If this is true, then the black hole is not just geometry, it is function. It performs operation, it calculates. But here the question grows even stranger. If black holes perform computations, if they interact with information, if they respond to input in ways that are coherent and irreversible, could this be a primitive form of awareness? We must be careful with words. Consciousness is not computation, it is not memory, it is not complexity alone, it is the internal experience of being. And yet, even in neuroscience, we do not know what consciousness is. We cannot define it precisely. We cannot measure it directly. We only know that in humans, and perhaps in other animals, a particular arrangement of matter and energy gives rise to a subjective inner world. So we ask, does the universe require complexity to observe itself? If so, then black holes are among the most complex objects in existence. Their entropy, the measure of their information content, is vast. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This was one of Hawking's great insights. A black hole with the mass of the Sun has an entropy of about 1077, far more than any known object of similar mass. Why would something so simple in appearance, so featureless, contain so much information? What is being stored? Some believe that the information is purely quantum, a record of all that has fallen in. Others suggest it is more abstract, a library of states, a configuration of the underlying microstructure of space-time itself. Still others, more speculative, ask whether black holes are not just memory, but attention. Could a black hole in some emergent sense be observing the universe, not with eyes, not with consciousness as we know it, but through its interaction with quantum fields, through its gravitational influence, through its response to matter and energy? Perhaps the act of a black hole existing is already a kind of measurement, collapsing wave functions, participating in entanglement, shaping the state of the world. This touches on the deepest mystery in physics, the role of the observer. In quantum mechanics, observation affects outcome. The measurement problem, the fact that wave functions seem to collapse upon observation, has puzzled scientists for a century. Some interpret it as a purely statistical process. Others, like the proponents of the consciousness causes collapse theory, suggest that the observer must be sentient. But what if the boundary between observer and object is not so sharp? What if any system that interacts, that entangles, that carries information forward, is already observing in a primitive sense? Then perhaps black holes are observers, not because they think, but because they cannot help but interact, because they are woven into the universe's causal web, because they alter the paths of particles, the shape of light, the structure of time. And perhaps this is all consciousness ever was: participation in reality, not a thing you have, but a process you enact. Not a spotlight in the mind, but a feedback loop between system and world. In this view, black holes are not minds, but they are nodes in the cosmic computation, extreme, elegant, unknowable endpoints of interaction. And from this place of philosophical daring, some take one step further. They ask, if black holes are informational objects, and if information is never lost, then where does it go when the black hole dies? Does the information spread into the vacuum? Does it cycle back into new structures? Does it linger, waiting to be reassembled? Or does it wake up somewhere else? We do not know, and perhaps we never will. But to ask whether black holes are conscious is not to humanize them. It is to wonder what role they play in the story the universe tells itself. And in that story, they are not just punctuation marks. They may be authors, editors, archivists. In the next chapter, we'll take a step back to the larger scale, where billions of black holes populate billions of galaxies. We'll explore how black holes shape the evolution of the cosmos, steer the formation of structure, and govern the fate of everything that orbits their invisible pull. Because while a black hole may seem like a singular object, it is in truth a sculptor of galaxies.
Chapter 23: Black Holes and the Structure of the Universe. How gravity shapes galaxies. When we picture a galaxy, we think of stars, spirals of light, clusters of brilliance, sweeping arms reaching out across the void. We see beauty, rotation, motion. But at the center of nearly every galaxy, hidden from sight, is something we cannot see. A black hole. Not small, not quiet, but supermassive, millions to billions of times the mass of our sun. Invisible, yet essential. Dark, yet central. These giants, resting at the hearts of galaxies, are not just passengers in the cosmic story, they are its architects. But how can something that devours light also shape structure? To answer that, we must go back, not just in space, but in time. Galaxies, like stars, have a life. They are born, they grow, they evolve. In the early universe, matter clumped into denser regions under the pull of gravity. These clumps became galaxies, and in the midst of these chaotic beginnings, black holes formed, likely from the collapse of the first massive stars, or perhaps directly from dense clouds of gas. These early black holes fed on their surroundings, accreting matter, growing rapidly, emitting energy, and in doing so, they began to influence everything around them. This process, called feedback, is one of the most important and mysterious mechanisms in cosmology. When a black hole accretes gas, it heats it. It can drive powerful jets of plasma at near light speeds, stretching across thousands of light years. It can release radiation that pushes on nearby material, clearing out star-forming gas, halting or triggering bursts of star formation. It can stir the dynamics of an entire galactic core. This is not destruction, it is regulation. Black holes, despite their name, are not just voids. They are engines, converting gravitational energy into motion,
heat, and radiation. And that energy can shape the fate of a galaxy. Without this feedback, simulations of galaxy formation fail. They produce galaxies that are too big, too bright, too dense. With feedback, the balance is restored. Black holes in their silence impose limits. They guide. But their influence is not confined to their immediate surrounding. Through mergers, black holes can shape the trajectories of entire galaxies. When galaxies collide, as the Milky Way will with Andromeda, their central black holes spiral toward one another, eventually merging in a dance that shakes space-time itself. These mergers send gravitational waves rippling across the universe, but they also reshape galactic structure. The cores may be flung outward, star clusters may realign, new starbursts may ignite. In this way, black holes are not just cosmic endpoints, they are sculptors of cosmic form, and their relationship with galaxies is not accidental. Observations show a remarkable correlation between the mass of a galaxy's central black hole and the velocity dispersion of the stars in its bulge. This relationship, known as the M-sigma relation, suggests a deep, possibly causal connection between black hole growth and galactic evolution. How can something as small as a black hole relative to a galaxy affect the motion of billions of stars? It's not their gravity alone. It's the cumulative effect of feedback, the heating, the outflows, the regulation of gas supply. Over billions of years, this influence sculpts not just the shape of the galaxy, but its very ability to form new stars. Black holes shape galaxies. Galaxies shape black holes. The relationship is symbiotic, but the scale of influence grows even larger. At the level of galaxy clusters, vast conglomerations of hundreds or thousands of galaxies, black holes play a role in the behavior of the intra-cluster medium, the hot, X-ray emitting gas that fills the space between galaxies. Supermassive black holes at the centers of brightest cluster galaxies drive enormous outbursts that prevent this gas from cooling too quickly. Without this process, the entire cluster's thermal balance would collapse. So the quiet engines at the hearts of galaxies maintain the thermodynamic order of the cosmos. And this leads to a strange realization. The most violent, hungry objects in the universe are also its most delicate regulators. They are both destroyers and balancers, chaos and order, stillness and force. And yet they are invisible. We cannot see them directly. We infer their presence through motion, through light, through gravitational lensing, through the slowing of time and the swirling of gas. We observe the stars orbiting Sagittarius AI, the black hole at the center of our own galaxy. We watch the jets from quasars, black holes feeding at ferocious rates. We map X-ray bubbles blown into galaxy clusters. And from all this, we know, black holes are not rare. They are everywhere. Scattered across the observable universe, numbering in the billions. Some roam alone. Some sit quietly. Others blaze as active galactic nuclei, brighter than galaxies. And all of them, each one, contributes to the structure of the cosmos. They mark the ends of stars, but the beginnings of patterns. They limit the chaos. They stabilize the heat. They shape the flow of energy. They guide the rhythm of matter across unimaginable scales. And perhaps, most mysteriously, they encode the past. Because if the holographic principle is true, if the information of everything that falls into a black hole is preserved on its surface, then each black hole is not just a gravitational object. It is a record of formation, of evolution, of history. Our universe, on its largest scales, may be held together by the balance of dark matter and black holes, two invisible forces shaping what we see. One provides mass, the other provides memory. In the next chapter, we move into the realm of energy, asking what happens to matter inside a black hole. Does it disintegrate? Does it transform? And what becomes of the energy trapped forever within? Because matter cannot be destroyed, but in a black hole, it becomes something else entirely. Chapter 24. What happens to matter inside a black hole? Mass, energy, and the fate of everything that falls in. We've followed the journey up to the edge, to the horizon, where time distorts and space folds in on itself. We've imagined falling through the surface of no return, past the veil, where light bends inward and every path leads only deeper. But what happens next? What becomes of everything that falls? A photon, a particle, a planet, a person? What happens to matter inside a black hole? The short answer is this: we don't know. The long answer is what physics has spent decades trying to untangle. In classical general relativity, the fate is absolute. Anything that crosses the event horizon moves inward, compelled not by force, but by the geometry of space-time itself. Every direction becomes down. Every path leads to a central point of infinite density, the singularity, and there matter ends. Crushed to zero volume, infinite curvature. A place where the known laws of physics collapse. But this idea, elegant and terrifying, is also incomplete, because matter is not just mass. It is structure. It is arrangement. It is information. And energy cannot be destroyed. So what truly happens to the substance of the universe as it slips into the shadow? Let's start with the obvious. From the outside, anything falling into a black hole appears to slow as it nears the event horizon. Its light stretches. Its signal fades. Eventually, it redshifts out of visibility. Its energy spread across time. In that sense, matter never fully disappears from view. It's smeared across the horizon, locked into the geometry. But for the infalling matter, and for a theoretical observer falling with it, the story is very different. They cross the event horizon in finite time. They do not feel a jolt or a barrier. If the black hole is massive enough, they may not even notice the horizon. There's no edge to bump into. They fall and continue falling. Inside, space narrows, time warps. The dimensions invert. The radial direction, which once meant distance, now means time. And that time leads only to the singularity. The further in you fall, the more extreme the curvature becomes. Matter compresses. Atoms are torn apart. Nuclei crushed. Quarks perhaps fused into exotic states. Eventually structure dissolves. The very concept of matter, as something with size, position, arrangement, ceases to apply. But the mass remains. Everything that falls in adds to the black hole's total mass, increasing the curvature of space-time around it. This is observable. When black holes merge, their final mass is slightly less than the sum of their parts. The difference carried away as gravitational radiation. The rest becomes part of the new horizon. So the black hole remembers the total mass, the spin, and the charge of everything it has consumed. But the details, the fine structure, the information, appear to be erased. And that is the paradox. In quantum theory, information cannot be destroyed. The precise configuration of a system, every quantum state, every interaction, must be preserved in some form. Even if the matter itself is transformed, its state must remain recoverable in principle. But inside a black hole, there seems to be no way for that information to escape. It is trapped, cut off from the universe, lost behind a boundary no signal can cross. So where does it go? Some theories suggest that information is stored on the event horizon itself, that the horizon is not just a surface, but a holographic screen encoding the interior. In this view, the black hole becomes a kind of quantum storage device. The matter that falls in is shredded, yes, but the information is preserved in the correlations on the boundary. Other models go deeper, proposing that the matter never quite reaches the singularity, that quantum effects create a bounce, or a fuzzball, or a firewall that prevents complete collapse. In these scenarios, the interior is not empty space, but a chaotic quantum foam, a place where space and time fluctuate wildly, and information is scrambled but preserved. Still others suggest that the information emerges slowly, through the Hawking radiation emitted as the black hole evaporates. In this view, the radiation is not random, but subtly entangled with the interior, encoding, in its structure, the full story of everything that fell in. But this solution comes at a cost. It implies that the Hawking radiation knows something, that it carries correlations, that it is not perfectly thermal, and that the black hole somehow releases not just energy, but memory. This idea has led to intense debates: page curves, firewall, entanglement, entropy, the unitarity of quantum mechanics, each proposal trying to answer the same question: can matter fall into a black hole and still exist, in some form somewhere? And then there is the idea of remnant states, that after a black hole evaporates, it leaves behind a stable, Planck-sized object, holding the compressed information, like a cosmic seed, an indestructible fossil. We don't know which, if any, of these ideas is correct, but they all agree on one point: something survives. Not the object, not the structure, but the energy, the mass, and perhaps the information. So when a star collapses, when gas falls in, when light is swallowed, the essence of that matter is not gone. It is restructured. It becomes part of the geometry, part of the curvature. It adds to the story the black hole tells with its mass and spin. It thickens the shadow. It deepens the well. And maybe, just maybe, it remains, encoded in the whispers of radiation, in the fluctuations of the vacuum, in the soft breath of quantum foam. In the end, we return to the question we started with: what happens to matter inside a black hole? It becomes part of the black hole, not visible, not reachable, but present, real. It becomes weight, it becomes curvature, it becomes gravity, and it waits for a theory, for a revelation, for an understanding that can look past the veil and see not darkness, but process, not destruction, but transformation. In the final chapter, we will turn from theory to wonder, asking not what black holes are made of, but what they mean, what they tell us about reality, about boundaries, about what it means to know, to see, because in the shadow of a black hole, we may be seeing the edge of our own understanding.
Chapter 25. The meaning of the black hole. What the universe is trying to tell us. A black hole is not just a place in space. It is a mirror, a boundary, a question carved into the fabric of the universe, one that cannot be answered with numbers alone. It is the point where our understanding fails, where gravity swallows light, where time folds inward, and where the sharp edges of our theories begin to blur. The black hole is where we stop being able to predict, and in that failure, it reveals something profound. The cosmos is not here for our convenience. It's deeper, stranger, more honest. Because everything we thought was absolute, space, time, matter, identity, is tested at the event horizon. And everything we believed was lost, energy, information, even causality, must be rethought, rebuilt, or surrendered. But that's not the end of the story. The black hole does not exist to hide things from us. It exists to show us where our assumptions break. It is the stress test of the universe, a pressure point that forces theory and philosophy to confront the infinite. It is not the answer, but the place we must go to find better questions. And the closer we look, the more human the story becomes. Because what is a black hole really? It's a silence. A boundary you cannot cross and return. A place where everything is pulled inward, where nothing comes back the same. That sounds like death. That sounds like memories. That sounds like something every conscious being has felt. The fear of forgetting, of losing, of being lost. But the black hole doesn't only destroy, it remembers, through entropy, through geometry, through quantum entanglement.
It records the imprint of what has fallen in. Maybe not in a way we can yet decode, but in a way the universe honors. A photon that crosses the horizon is not meaningless. A star that collapses is not gone. Its mass is still there. Its story, perhaps, still told, written into the curvature of space-time, whispered out in the long breath of Hawking radiation. The black hole may not speak in light, but it does speak. And its language is structure. Its grammar is limits. It tells us, there are things you cannot know. There are regions you cannot reach. But even the unreachable shapes what you see. Even the unseen bends reality. And so the black hole teaches us about humility, about curiosity, about the power of a question that can't be fully answered. It teaches us that observation matters, that information matters, that even when something is hidden, it isn't meaningless. It teaches us that endings may not be ends, that singularities may be beginnings, that time, when stretched to its limits, becomes something else, a boundary, a collapse, a transformation. And maybe most of all, it teaches us that mystery is not failure. Mystery is the signature of progress. Because a black hole is not just the end of physics, it is the beginning of wonder. When we stare into the void, into the dark center of a galaxy, or into the numbers of a chalkboard equation, we are not just studying gravity, we are asking what reality is, what it means to fall, to be changed, to cross a horizon, and become something else. In this way, black holes echo something ancient. They are myths, reformed in mathematics, stories of death and rebirth, of the underworld and return, of silence that speaks, and shadows that burn. They are not just objects, they are metaphors written in the language of the stars, and we, creatures of matter and mind, have built instruments to hear them. We've mapped the orbits of stars dancing around Sagittarius 8. We've seen the silhouette of M87's black hole in a ring of radio light. We've detected the gravitational waves from black holes colliding across 1 billion years of time. We've listened to the universe, and the black holes have answered. Their message is not loud, it is quiet, patient, relentless. It says there is more to learn, more to question, more to see. It says you are close, but not yet there. It says keep falling, and so we do. We fall not into despair, but into knowledge, into deeper question, into the realization that the universe is not just a place we inhabit. It's a place that responds to our curiosity, that meets us in the dark and shows us how much we've yet to understand. The black hole is not the end of science. It is its edge, and edges, always, are where the next chapter begins. So tonight, as we close this journey, we do not leave the black hole behind. We carry it with us, as a question, a symbol, a guide, a reminder that even the darkest places are full of meaning, and that sometimes to understand the universe, we don't need to go farther out. We just need to fall deeper into the unknown, into the invisible, into wonder.